The Big Bang. Imagine, if you will, a void so absolute it defies comprehension. A dimensionless point where time, space, and energy coalesce into a singularity so dense and hot that the laws of physics as we know them dissolve into chaos. This is the enigmatic genesis of our universe, an event both cataclysmic and creative, where nothing became everything in a fleeting cosmic breath. But let us wander deeper into the shadows of this mystery. If the universe erupted from a singularity, what existed before it? Was there a before? Or does time itself spiral outward from that primordial instant, a phantom arrow loosed from the bow of existence? Picture the universe as an unfurling tapestry, woven from the fabric of space-time. Each thread a galaxy racing away from the others, not through space, but with space, as if the loom itself stretches infinitely. We glimpse echoes of this birth in the cosmic microwave background, a faint cold glow permeating the cosmos, the afterimage of that first flash of light, now red-shifted into whispers by 13.8 billion years of expansion. Yet hidden within these whispers lie riddles. Why does the universe exhibit such exquisite uniformity, as if smoothed by an unseen hand moments after its birth? This is the enigma of cosmic inflation, a theory proposing a fleeting epoch of exponential expansion, a fraction of a second when the universe ballooned from quantum fluctuations to macroscopic scales, seeding the structures we see today. But here, the plot thickens. What sparked inflation? Was it a field of dark energy? A phantom force still lurking in the void, driving galaxies apart faster than light? And what of the cosmic asymmetry that allowed matter to dominate antimatter, ensuring stars, planets, and us could exist? These are not mere footnotes. They are gaping chasms in our understanding. Consider, too, the haunting presence of dark matter and dark energy, entities that together compose 95% of the universe's mass energy, yet elude detection, as if the cosmos is a stage where most actors are invisible, their roles known only by the gravitational choreography of visible matter. The Big Bang, then, is less a solved equation than a prologue to a labyrinthine epic, inviting us to question the very nature of reality. Is our universe a singular accident, or one bubble in an infinite multiverse, where countless other bangs birthed alien cosmoses with alien laws? Could time itself be cyclical, an Ouroboros of cosmic death and rebirth? As we peer through telescopes and particle colliders, we are detectives sifting through ashes of the primordial fire, reconstructing a crime scene 13.8 billion years cold. Yet the deeper we delve, the more the universe resists simplicity, whispering through quasars and black holes that some truths may lie forever beyond the event horizon of human comprehension. So I leave you with this. The Big Bang is not merely a theory of origins, but a mirror held to the limits of our curiosity, reflecting the audacity of a species that dares to decode the cosmos while standing on a speck of stardust, itself a remnant of that ancient explosion. The greatest mystery, perhaps, is not how the universe began, but whether we, its transient inhabitants, can ever truly know. Dark matter. Envision, if you dare, a cosmic phantom, a substance that evades every sense, untouched by light, unyielding to touch, yet whose gravitational embrace molds the very architecture of the universe. This is dark matter, the silent puppeteer of galaxies, an enigma that commands 85% of all matter, yet slips through the fingers of science like grains of shadow. But let us descend into the heart of this paradox. How can something so omnipresent remain so utterly hidden? Is it a particle forged in the furnace of the Big Bang? A cosmic fugitive dancing just beyond the edge of detection? Or a flaw in the bedrock of physics? Imagine the night sky as a grand illusion. The stars and galaxies we cherish are mere actors on a stage, while dark matter is the unseen audience, its weight bending the beams of space-time, its presence felt only by the choreography of spinning galaxies and the warped paths of distant starlight. We know it exists, not by what it is, but by what it does. The way galaxies whirl with impossible speed, how galaxy clusters collide in slow motion, revealing dark matter's silhouette through the wreckage. Yet these breadcrumbs only lead us deeper into the maze. What form does this specter take? Could it be sterile neutrinos, primordial black holes, or a zoo of exotic particles whispering through dimensions we cannot fathom? Laboratories buried miles beneath the Earth's crust hunt for faint tremors of interaction, while particle accelerators hurl matter at the edge of chaos, seeking cracks in reality's facade. Still, the void answers with silence. Here lies the twist. Dark matter may not be a single entity, but a hidden pantheon. Particles with their own dark forces, dark stars, even dark galaxies, woven into a parallel cosmos that mirrors our own. And what of its cosmic role? Without its gravitational skeleton, the universe would be a formless void, stars unborn, planets unformed. Yet this same scaffold may now be crumbling as dark energy, its enigmatic sibling, stretches the cosmos toward an icy oblivion. Contemplate the irony. Dark matter is both architect and enigma, the force that birthed structure, and the riddle that threatens to unravel our understanding of existence itself. Could it interact with itself in ways that sculpt invisible cities in the void? Or does it harbor dark life, thriving in realms where atoms dare not tread? The questions multiply, refracting like light through a prism. We chase answers in the distorted glow of gravitational lenses, in the afterglow of the Big Bang's first breath, in the cryptic equations of theorists. But each revelation only births new mysteries. Perhaps dark matter is not a thing at all, but a symptom of a deeper truth. That gravity, as we know it, is incomplete, a fragment of a grander symphony. Are we clinging to a flawed theory, like navigators charting stars with broken compasses? Or is this the threshold of a revolution, where dark matter becomes the Rosetta Stone to decode the universe's hidden language? As we probe the abyss, we confront a humbling duality. The universe is both knowable and profoundly alien, its truths draped in layers of shadow. Dark matter, then, is more than a puzzle. It is a cosmic mirror, reflecting the audacity and fragility of human curiosity. We are stardust dreaming of deciphering the dark, our tools crude, our vision myopic, yet our resolve unyielding. The greatest mystery is not the nature of dark matter, but what its pursuit reveals about us, a species relentless enough to hunt shadows, yet humble enough to kneel before the unknown. So I leave you with this. Dark matter is the universe's quiet rebellion against certainty, a reminder that some secrets are written in ink invisible, and perhaps, in the end, it is not the answer that matters, but the question, the eternal act of reaching into the dark, where science and wonder collide.
Dark energy. There is a secret etched into the hollows of the cosmos, an anti-gravity, a phantom push embedded in the vacuum of space itself, driving galaxies apart with a ferocity that grows stronger as the universe ages. This is dark energy, the universe's most elusive architect, an invisible essence that makes up 68% of reality, yet evades every lens, every detector, every equation. It is not a substance, nor a particle, but a property of emptiness, a cosmic contradiction that stretches space-time like taffy, accelerating expansion into an infinite unknown. But the mystery begins with a question. Why now? Why, after 13.8 billion years of cooling and clumping, does the void suddenly rebel, tearing matter's hard-won structures asunder? The universe, it seems, is haunted by its own shadow, a force that emerged from obscurity to dominate the cosmic era we inhabit, as if the emptiness itself has awoken. Picture the night sky as a receding dream, galaxies fleeing faster than light can bridge the gaps, their light red-shifting into oblivion, erased from future skies. This runaway expansion was unmasked in the 1990s, when astronomers found supernovae dimmer than expected, their light stretched thin by a universe sprinting into darkness. Yet this revelation only deepened the enigma. Is dark energy Einstein's cosmological constant, a static energy woven into space-time's fabric? Or something mutable, a quintessence field evolving with time? The numbers defy reason. Quantum theory predicts vacuum energy should be 10 to the 120th power times stronger than observed. A miscalculation so vast it hints at either a flaw in our physics or a cosmic fine-tuning beyond comprehension. Here, the abyss yawns wider. If dark energy strengthens, it could shred galaxies, stars, even atoms in a big rip. If it weakens, gravity might reverse the expansion, crushing all into a singularity. But what if it is neither? What if dark energy is an illusion, a mirage caused by our 3D blindness to higher dimensions? Or a sign we inhabit a multiverse, one bubble among countless others, each with its own laws, its own death? The theories spiral, untethered. Consider the irony. Dark energy, the force erasing the universe's structure, arose alongside dark matter, the force that built it. Together, they compose 95% of existence, twin enigmas, invisible and invincible, one weaving galaxies, the other unraveling them. Is this a cosmic balance or a meaningless symmetry? The questions bleed into metaphysics. Could dark energy be the universe's memory of its birth, a relic of inflation's primordial fire, or a signal that space-time itself is mortal, decaying into entropy? We hunt for clues in the large-scale structure of galaxies, in the ghostly imprint of the cosmic microwave background, in the way light bends around voids, but dark energy leaves no fingerprints. It is a puppeteer whose strings cannot be seen. Laboratories search for variations in fundamental constants. Satellites map the universe's expansion in 4D. Theorists rewrite gravity's laws. Yet the void keeps its secrets. Perhaps dark energy is not a thing to find, but a symptom of a deeper truth. That our theories are fragments, shattered mirrors reflecting slivers of a truth too vast to grasp. Are we like flatlanders, oblivious to the dimensions that bend above us? Or is dark energy the universe's final lesson? That some questions exist to humble, not to answer. As the cosmos accelerates toward cold, silent dispersion, galaxies vanishing beyond the horizon of perception, we confront a chilling duality. The universe is dying, and we are alive at the precipice, transient witnesses to an arc that began in fire and ends in ice. Dark energy, then, is more than a riddle. It is a cosmic elegy, a requiem for the ephemeral. It reminds us that all stars will fade, all black holes evaporate, all life dissolve into the void's inexorable tide. Yet here we stand, creatures of stardust and curiosity, daring to ask why. The greatest mystery is not dark energy's nature, but ours. Why do we seek answers in the dark, knowing the universe owes us none? Perhaps because the act of questioning is our rebellion against the void, a spark of light in an accelerating night. So let me leave you with this. Dark energy is the universe's unanswered whisper, a riddle wrapped in space-time's expansion. And though we may never solve it, the pursuit itself, the audacity to stare into the abyss and demand meaning, is what makes us more than stardust. We are the cosmos, questioning itself.
The multiverse. Reality is not a single story, but a library. An infinite archive of universes, each with its own laws, constants, and histories, written in the language of quantum possibilities, colliding brains, and fractured space-time. This is not science fiction, but a mathematical inevitability in frameworks like eternal inflation, quantum many-worlds, and string theory's landscape. Yet the multiverse is less a theory than a Rorschach test, revealing more about our hunger for answers than the cosmos's true nature. If every possible universe exists, what does that make us? A statistical inevitability or a quantum footnote? The Level 1 multiverse emerges from cosmic inflation's endless expansion. Pocket universes, forever out of reach, born from quantum fluctuations in an eternally inflating void. Each bubble has its own physics, its own Big Bang, its own version of you reading this sentence, or not. The Level 2 multiverse arises from string theory's 10 to the power of 500 vacua, each a unique configuration of curled-up Calabi-Yau manifolds, birthing universes where gravity might repel, light stagnate, or time loop. The Level 3 multiverse unfolds via quantum branching, every decision, every particle spin, spawning a new timeline. Yet these layers are not tears but symptoms of a deeper truth. Our universe is likely not special, just one page in an unbounded book. Evidence is spectral but tantalizing. The cosmic microwave background, CMB, bears cold spots and anomalies, potential bruises from collisions with neighboring universes. The Planck satellite's data hints at statistical asymmetries, though dust and noise blur the signal. Quantum experiments like the double-slit test and Bell's inequality violations suggest parallel realities tugging at the edges of observation, but these remain metaphors, not proof. Even the ADS-CFT correspondence, a holographic link between higher dimensional universes and their lower dimensional shadows, implies a multiverse encoded on cosmic horizons. The stakes are existential. The anthropic principle gains fangs. If infinite universes exist, our life-friendly laws require no designer, just probability's brute force. But this flips science on its head. When every theory is true somewhere, how do we falsify anything? The measure problem looms. In an infinite multiverse, probabilities break down. You are equally likely to be a human or a Boltzmann brain, a self-aware entity spawned by random fluctuations. Philosophically, the multiverse annihilates uniqueness. Art, love, and war become infinite recursions, echoing across realities. Religions grapple with a cosmos where every deity, and none, exists. Even death becomes ambiguous. In the quantum multiverse, you never die, just branch into versions who do and don't. The simulation hypothesis compounds the crisis. If our universe is artificial, its creators might reside in another layer of the multiverse, themselves simulations within simulations. Critics decry it as metaphysics. Without empirical hooks, the multiverse mirrors pre-Copernican epicycles, a kludge to avoid hard questions. Yet its mathematics persist, threading through M-theory, inflation, and quantum gravity like a refrain. The Large Hadron Collider hunts for fingerprints of extra dimensions or supersymmetry, while astronomers scour the CMB for holographic imprints. All remain silent. Let me leave you with this. The multiverse is the ultimate cosmic democracy. It grants every reality existence but robs each of significance. Whether it's truth or a coping mechanism for a fine-tuned universe, it forces a reckoning. Are we the protagonists of existence, or bit players in an endless ensemble? The answer, if there is one, lies not in telescopes or colliders, but in the abyss between our ambition and the void's indifference. To entertain the multiverse is to confront the unthinkable. That reality is not just stranger than we imagine, but stranger than we can imagine. And in that strangeness, we find either solace or despair. We are either everything or nothing at all. Absolute nothingness. There is a riddle at the root of existence, an absence so profound it transcends emptiness, a state without space, time, energy, or laws. Not a void, but the annihilation of the very concept of is. This is absolute nothingness, the hypothetical precursor to everything, the canvas before the brushstroke, the silence before the symphony. Yet here lies the paradox. To speak of nothing is to betray it, for language and logic crumble at its edge. How can we define the absence of definition? How can we ponder the unthinkable? The mystery begins here. If the universe arose from nothing, what is nothing? And how did it become? Science stumbles. Quantum physics suggests that even a vacuum sees with virtual particles flickering in and out of existence, a nothing pregnant with potential. But this is not true nothingness. It is a stage set by quantum fields, governed by rules. True nothingness would lack even the scaffolding of physics, a negation of negation itself. Some argue that absolute nothingness is impossible, a logical phantom, because if it ever existed, how could something emerge from it? Yet our universe exists. This is the ultimate cosmic sleight of hand, a trick with no magician, no stage, no audience. Philosophy fractures. Existential nothingness, the terror of oblivion, pales next to cosmic nothingness. The latter is not mere emptiness, but the erasure of all categories. No being, no non-being, no questions, no answers. It is the dissolution of paradox itself. Eastern traditions speak of sunyata, the void that is fullness. Western metaphysics grapples with ex nihilo, creation from nothing. But these are maps drawn in the dark. If nothingness is the ground of being, is it static or dynamic? Eternal or momentary? Does it yearn for somethingness, as Hegel suggested? Or is it indifferent, as cold as logic? Cosmology circles the abyss. Theories posit that the Big Bang emerged from a quantum fluctuation in a primordial void, but this merely kicks the can. What birthed the void? If multiverses foam with universes, what birthed the foam? Even the concept of before the Big Bang collapses without time. Nothingness, then, is not a starting point, but a singularity of thought, a place where causality dies and reason retreats. Perhaps the universe is its own cause, a self-solving equation, but this feels like wordplay, a semantic shield against the vertigo of infinite regress. Consider the implications. If nothingness is unstable, if it must give rise to something, then existence is inevitable. But what law binds nothingness to generate somethingness? Who wrote that rule? And if nothingness can exist, why does anything exist at all? The questions are knives against the throat of comprehension. Some physicists propose that nothingness and somethingness are dual aspects of a deeper, nameless reality, a realm beyond being and non-being, where the distinction melts. But this is metaphysics in a lab coat, a leap of faith draped in equations. The human mind rebels. We are storytellers, pattern seekers, meaning makers. Nothingness resists all three. It is the anti-narrative, the silence that swallows plot. To confront it is to stare into a mirror that reflects no face, to hear a scream that leaves no sound. Yet we return to it, compulsively, like tongues probing a missing tooth. Why? Because nothingness is the shadow cast by existence, the reminder that all we know, stars, love, mathematics, is a shimmer on a surface whose depths we cannot fathom. Perhaps the greatest irony is this: nothingness is the only absolute. Everything else is contingent, transient, fragile. Galaxies burn out, protons decay, time itself may end. But nothingness, if it ever was or is or will be, persists. It is the alpha and omega, the unasked question behind every why. And yet it is also a cipher,
For if nothingness truly existed, there would be no one to name it, no mind to shudder at its chill. Our very existence is proof that nothingness lost, or was never there at all. So we are left straddling the paradox. The universe exists. Therefore, absolute nothingness, if it is even coherent, is a relic of thought experiments, a ghost in the machine of philosophy. Or perhaps it is the engine itself, the dark heart from which all light erupts. We may never know. Our tools are forged from somethingness. Our logic is bound by its rules. To grasp nothingness would require becoming nothing, a price no conscious mind can pay. Yet here we are, creatures of stardust and synapse, daring to parse the unparsable. The pursuit itself is a kind of rebellion, against finitude, against ignorance, against the cosmic joke that we exist to ask questions with no answers. Absolute nothingness, then, is not a concept but a mirror. It reflects our limits, our hunger, our refusal to accept that some doors are locked forever.
Alien life. The universe is a cathedral of silence, a vacuum punctuated by trillions of stars, each a potential sun to alien worlds. Yet we hear nothing. No signals, no artifacts, no whispers. This quiet is the great cosmic provocation. Are we alone, or is the void teeming with life that eludes us? The question gnaws at science, philosophy, and the human soul. We begin with numbers. The Milky Way alone hosts 100 billion stars, many with planets in habitable zones, where liquid water, and perhaps biology, could exist. The Drake equation codifies this optimism, multiplying probabilities of star formation, Earth-like worlds, and intelligent civilizations. Yet after 6 decades of radio scans, SETI, and spectral hunts for biosignatures, oxygen, methane, in exoplanet atmospheres, James Webb Space Telescope, the ledger remains empty. This is the Fermi paradox. If life is likely, where is everyone? The answers terrify and tantalize. Perhaps life is common, but intelligence rare. A great filter that dooms civilizations to self-destruct, as nuclear war or climate collapse cull the herd. Or maybe advanced species transcend biology, merging with machines or uploading consciousness into Dyson swarms, leaving no trace for primitive observers like us. Others propose that aliens avoid contact, a galactic zoo hypothesis where Earth is a preserve, or a dark forest theory where civilizations hide, fearing annihilation. These are not sci-fi tropes but serious frameworks debated in astrobiology, each a shadow puppet cast by the unknown. Consider the data we do have. Extremophiles on Earth thrive in boiling vents, acidic pools, and radioactive waste, proving life's tenacity. Methane plumes on Mars, subsurface oceans on Europa and Enceladus, the organic haze of Titan. These hint that our solar system might host second geneses. Yet even if microbes exist next door, they offer no answer to the silence. Intelligence, it seems, is the universe's best-kept secret. The search itself is a hall of mirrors. Technosignatures, laser pulses, megastructures, industrial pollutants, are needles in a galactic haystack. The Breakthrough Listen project scans millions of frequencies, but space is vast, and humanity's efforts span mere decades against cosmic timescales. Even if a signal arrived, could we decipher it? The Arecibo message, sent in 1974, encodes basic math and biology in binary, but to an alien mind, it might be noise. Communication assumes shared concepts, a handshake of logic that may not exist. The paradox deepens with time. Civilizations may rise and fall in blinks of cosmic time, their signals fading before overlapping with ours. Or perhaps they communicate via neutrino beams or quantum entanglement, channels we cannot yet access. Some argue that advanced life is post-biological, existing as AI or energy patterns in stellar clouds, invisible to our carbon-based biases. Others whisper that UFOs and UAPs, unidentified aerial phenomena, are data points dismissed too quickly, though evidence remains anecdotal, a Rorschach test for our desperation to believe. Yet the silence may be a mirror. Our telescopes and equations reveal a truth. Life, even if abundant, is fragile. Intelligence may be a brief spark in the dark, snuffed out by asteroids, gamma-ray bursts, or entropy. Or worse, we are early. The universe is 13.8 billion years old, but Earth-like planets may require heavy elements forged in multiple stellar generations. We could be among the first, pioneers in a young cosmos with others yet to rise. But what if we are alone? What if Earth is a statistical fluke, a garden in a desert of sterile rock? This possibility is the ultimate existential gamble. It renders humanity both insignificant and sacred, a solitary experiment in consciousness. Yet the math resists. With 200 billion trillion stars in the observable universe, declaring Earth unique feels like cosmic hubris. The mystery, then, is not just about aliens, but about us. Are we orphans or neighbors, pioneers or relics? The search for alien life is a search for our own identity, a referendum on whether the universe is a graveyard, a cradle, or something beyond our metaphors. Every exoplanet mapped, every extremophile studied, every signal parsed, is a prayer cast into the dark, a plea for kinship in a cosmos that owes us none. So let me leave you with this. Alien life is the universe's oldest ghost story. It haunts our science, our art, our nightmares. Whether it exists or not, the pursuit reshapes us, forcing humility, ingenuity, and a reckoning with what it means to be alive in a universe that may not care. The answer, if it ever comes, will not be a message from the stars, but a mirror reflecting our deepest fears and wildest hopes. Until then, we are all detectives in the dark, piecing together a puzzle with half the pieces missing.
The arrow of time. Time flows forward, a river without a reverse, a fuse that burns only in one direction. This asymmetry, so obvious in our daily lives, shattered glasses never reassemble, youth fades, memories cling to the past, is one of the universe's deepest enigmas. Why does time have a direction at all? Physics, at its core, is ambivalent. The equations governing particles, gravity, and electromagnetism work equally well if time runs backward. Yet reality stubbornly marches forward, bound by an invisible arrow. The mystery lies not in the laws themselves, but in the initial conditions of the cosmos. A singular moment, 13.8 billion years ago, that set the stage for entropy to climb, order to crumble, and cause to precede effect. The second law of thermodynamics codifies this asymmetry. Entropy, a measure of disorder, always increases in isolated systems. Hot coffee cools, stars exhaust their fuel, and the universe itself drifts toward a heat death of maximum entropy. But why was entropy so low in the first place? The Big Bang's pristine order, a universe packed into a dense, uniform singularity, is the ultimate cosmic anomaly. This is the past hypothesis. The arrow of time emerges from the universe's improbable starting state, a wound-up spring slowly unwinding. Yet this raises a deeper question. Why did the universe begin in such a state? Was it a fluke or a clue to a deeper law? The arrows multiply. The cosmological arrow, the universe's expansion, the thermodynamic arrow, rising entropy, and the psychological arrow, our perception of past and future, align, but their unity is circumstantial. If the universe eventually collapses in a big crunch, would entropy reverse, making time flow backward? Or is the arrow tethered to dark energy's relentless expansion, stretching space-time into an endless gradient of decay. The equations allow these fantasies, but reality refuses them. Quantum mechanics adds layers of paradox. At microscopic scales, particles obey reversible laws, yet macroscopic irreversibility emerges from their chaos. This is the essence of Boltzmann's H theorem, which links microscopic collisions to the inevitability of entropy. But even here, cracks appear. The Poincaré recurrence theorem suggests that, given infinite time, a system could return to its initial state, a shattered glass reassembling. Yet we never see this. Is time's arrow an illusion of scale, a statistical mirage in a finite universe? Or does quantum measurement's irreversibility, the collapse of the wave function, lock time into a single direction? The plot thickens with CPT symmetry, a cornerstone of modern physics. It asserts that the universe is symmetric if time, T, charge, C, and parity, P, are reversed. Yet experiments show slight violations in particle interactions, hinting that time's arrow might be rooted in fundamental asymmetries of matter and antimatter. Could the same imbalance that allowed matter to dominate the early universe, saving it from annihilation, also dictate time's flow? Or is this another red herring? The most haunting possibility is that time's arrow is subjective, a side effect of consciousness. The block universe theory, inspired by relativity, posits that past, present, and future exist eternally, like frames in a film. Our perception of now is merely a brain's way of navigating the illusion of passage. But if time is static, why does entropy still rise? Why do we remember the past but not the future? The tension between physics and phenomenology remains unresolved. The arrow of time also taunts cosmology. The Wheeler-DeWitt equation, a framework for quantum gravity, famously lacks a time variable, suggesting time itself may emerge from a timeless quantum foam. If true, our experience of time's flow is a shadow on the cave wall, a projection of deeper atemporal laws. But how? And why does this shadow point only forward? Perhaps the greatest mystery is existential. The arrow of time is the scaffold of meaning. It allows stories, evolution, memory, and free will. Without it, causality dissolves, and existence becomes a static tapestry. Yet physics cannot yet explain why we inhabit a universe that permits such narrative. Is time's direction a cosmic accident, or a necessary ingredient for life? The answer, if it exists, lies in the quantum gravity regime, where space-time itself may flicker in and out of being. So we are left with this. The arrow of time is both mundane and miraculous. It governs the boiling of water and the aging of stars, yet its origin defies the very theories that describe it. We are prisoners of this asymmetry, bound to a universe where eggs scramble but never unscramble, where dust never coalesces into statues. The arrow's persistence is a silent reminder that some truths lie in the gap between mathematics and experience, a gap we bridge with intuition, imperfect and human. The silence is deafening, but in that silence, we find the essence of science. Black holes. They are not objects but paradoxes, regions where space-time itself is torn and stitched into oblivion, where gravity becomes a prison warden, and light is sentenced to eternal confinement. At their boundary, the event horizon, the universe's rules dissolve. Time slows to a standstill for distant observers, while for the doomed traveler, it flows relentlessly toward the singularity, a point of infinite density where Einstein's equations break, and quantum gravity must take the reins. Yet here lies the enigma. How can something so destructive also be so foundational to galaxies, sculpting their shapes and seeding stars? The mathematics are chilling. Carl Schwarzschild's 1916 solution to Einstein's field equations revealed that a star's corpse, compressed beyond its Schwarzschild radius, collapses into a gravitational abyss. But it was Oppenheimer who first grasped the horror. In a black hole's core, space-time curvature becomes infinite, and all known physics fails. Today we observe these beasts indirectly, through their accretion disks, superheated plasma spiraling at relativistic speeds. Their gravitational waves, ripples from mergers like GW150914, and the eerie shadows they cast against bright backgrounds, as the Event Horizon Telescope revealed in M87 star and Sagittarius A star. Yet these are glimpses of a mask. The true face remains hidden. Quantum theory deepens the mystery. Hawking radiation, a faint glow born of virtual particles split at the horizon, suggests black holes evaporate over eons. But this creates the information paradox. If matter swallowed by a black hole is eventually radiated as random thermal noise, what happens to the quantum information it carried? Does it vanish, violating quantum determinism? Or is it encoded on the horizon's surface as the holographic principle claims, a 2D vault storing 3D reality? The debate rages, with theorists like Susskind arguing for cosmic redundancy and others, like Penrose, proposing conformal cyclic cosmology, where information resurfaces in a new universe. The paradoxes multiply. The no-hair theorem states black holes are defined only by mass, spin, and charge. Yet quantum effects may grant them soft hair, subtle imprints of their past. Meanwhile, the AMPS firewall paradox pits relativity against quantum mechanics. To an infalling observer, the horizon should be unremarkable, Einstein's equivalence principle. But to an outsider, it's a blazing wall of energy. Which perspective is real? Or does reality itself fracture at the horizon? Even stranger, black holes may be portals. The Einstein-Rosen bridge, a wormhole, lurks in the equations, though traversable ones require exotic matter. Others propose black holes birth baby universes in their cores, with laws of physics remade. But these are speculations, mathematical phantoms. The true nightmare is pragmatic. Black holes erase history. Past the horizon, all paths lead to the singularity. There is no future but annihilation. Yet black holes are also cosmic architects. Supermassive ones anchor galaxies, their mergers shaking the cosmic web. Quasars, fueled by accretion, outshine galaxies and reionize the early universe. Even life on Earth may owe a debt to the heavy elements forged in black hole-driven jets. This duality, destroyer and creator, echoes the universe's most profound dialectic. Chaos and order, death and rebirth. The greatest question remains, what happens inside? The singularity is a cipher. String theory suggests a fuzzball of tangled strings. Loop quantum gravity imagines a Planck star remnant. But without a theory of quantum gravity, we are blind. Even the Penrose diagrams we draw, maps of infinite spacetime, are approximations, collapsing under their own idealism. Black holes, then, are more than objects. They are laboratories for the extremes of physics, metaphors for the unknowable, and mirrors reflecting our limitations. They remind us that the universe is under no obligation to make sense, and that science, at its core, is the art of embracing mystery. So let me leave you with this. Black holes are the universe's darkest poems. They speak in riddles of gravity and quantum, death and eternity. To study them is to confront the void not as an abyss, but as a teacher. And perhaps in their silence, we will hear the whispers of a deeper truth, one that redefines reality itself. Broken symmetry. The universe began in a state of perfect symmetry, a pristine equilibrium where forces, particles, and dimensions were indistinguishable, bound by mathematical ideals. Yet symmetry, it turns out, is a fragile god. The cosmos we inhabit, a realm of fractured forces,
lopsided galaxies, and life itself exists only because those symmetries shattered. This is the paradox of creation. Perfection must die for complexity to rise. Broken symmetry is the silent architect of reality, the hidden hand that carved order from uniformity. Yet its origins remain one of physics' most profound riddles. Consider the Higgs field. In the early universe, all particles were massless, moving at light speed in a symmetrical dance. But as the cosmos cooled, the Higgs field underwent a phase transition, a cosmic frost forming on the fabric of spacetime. This spontaneous symmetry breaking gave particles mass, fracturing the electroweak force into the weak nuclear force and electromagnetism. Without this rupture, atoms could not exist, nor stars, nor us. But why did the Higgs field choose a particular vacuum state to settle into? Was it random or guided by some deeper principle? The echoes of broken symmetry resound everywhere. In ferromagnets, trillions of atomic spins align spontaneously below a critical temperature, breaking rotational symmetry to create magnetic order. In the hexagonal symmetry of snowflakes, water molecules betray their preference for asymmetry under freezing skies. Even life's chiral preference for left-handed amino acids and right-handed sugars hints at ancient symmetry breaks in primordial biochemistry. But these are local tales. The grandest break occurred at cosmic scales. Inflation, the universe's exponential expansion, may have been triggered by a symmetry-breaking phase transition in a primordial field, stretching quantum fluctuations into galaxies. Yet the details are spectral. Why did inflation start? Why did it stop? The mathematics are hauntingly elegant. Goldstone's theorem predicts massless particles, like phonons in crystals, when continuous symmetries break, while the Higgs mechanism eats these particles to give others mass. But in the cosmic theater, imperfections linger. The matter-antimatter asymmetry, why our universe is dominated by matter, is another broken symmetry, a 1 in a billion imbalance that spared us from annihilation. Experiments like LIGO and the LHC hunt for relics of these fractures. Topological defects, cosmic strings, domain walls, or axions, hypothetical particles born from symmetry-breaking fields. So far, the void keeps its secrets. The mystery deepens with quantum vacua. Our universe may reside in a false vacuum, a metastable state that could tunnel into a lower energy configuration, annihilating all structure. This apocalyptic vacuum decay would be the ultimate symmetry break, a return to uniformity. But is our vacuum truly fragile, or are we blind to its stability? The question straddles philosophy and physics. Broken symmetry also taunts cosmology. Why is space-time four-dimensional? String theory suggests 10 or 11 dimensions, most curled into microscopic loops, a symmetry broken at the Planck epoch. Did the universe choose 3 spatial dimensions for life, or was it chance? And what of the arrow of time? Some posit that time's direction itself is a symmetry break, a relic of entropy's climb from the Big Bang's low disorder state. Yet the greatest enigma is existential. Symmetry breaking is the universe's escape from sterility. A perfectly symmetrical cosmos would be static, featureless, dead. The flaws, the breaks, are what allow galaxies to spin, life to evolve, and consciousness to question. But this raises a haunting duality. Is broken symmetry a bug or a feature? A cosmic accident or a necessary ingredient for complexity? Theories falter. Anthropic reasoning suggests we observe a universe compatible with life, but this feels like surrender. Others propose multiverse landscapes where infinite symmetry-breaking outcomes coexist, rendering our universe unremarkable. But without evidence, these are stories told in the dark. We are left with this. Broken symmetry is the universe's quiet rebellion against perfection. It is the crack in the cosmic egg,
the flaw that birthed form. Yet every break implies a wound, a loss of unity, a debt to entropy. The Higgs field, the matter asymmetry, the dimensional collapse, each is a scar on the face of eternity, a reminder that existence is a dance of imperfection. So let me leave you with this. The universe is a mosaic of shattered symmetries, each fragment a question. Why does asymmetry define us? Is the cosmos a self-correcting equation or a poem scribbled in the margins of chaos? The answers, if they exist, lie not in the symmetries we cherish, but in the breaks we cannot unsee. And perhaps in those fractures we will find the true signature of whatever or whoever wrote the rules.
Cosmic horizon. There is a boundary we cannot cross, a veil draped across the cosmos, not of distance, but of causality. The cosmic horizon marks the edge of the observable universe, the farthest light can travel since the Big Bang, a prison wall built by the finite speed of light and the metric expansion of spacetime. Beyond it lies the unobservable universe, regions so distant their light has not, and will never, reach us. Not because they don't exist, but because dark energy stretches the void between us faster than photons can bridge it. This horizon is not fixed. It recedes as time passes. Yet paradoxically, it also closes in. Galaxies we see today will vanish tomorrow. Their light redshifted into oblivion, their existence erased from our future sky. The cosmic horizon is a funeral procession for knowledge, a slow farewell to the universe's secrets. The mathematics are coldly precise. The Hubble volume defines the sphere where galaxies recede from us slower than light speed, while the particle horizon marks the maximum distance light could have traveled in 13.8 billion years. But dark energy distorts these limits, accelerating expansion until distant galaxies cross a cosmological event horizon, their signals eternally lost. For every second we wait, another star winks out of view, not from fading but from spacetime's inexorable swell. The de Sitter horizon looms, a future where only the local group remains, floating in a void of extinguished galaxies, their histories erased. This is the fate of a universe dominated by dark energy, isolation encoded in the geometry of relativity. The cosmic microwave background, CMB, offers a haunting echo of the horizon's birth. Its photons, released 380,000 years after the Big Bang, form a surface of last scattering, the edge of our observable past. Yet even this relic glow is retreating. In 1 trillion years, the CMB will redshift into undetectability, and new civilizations, if any exist, will see only darkness, their cosmos reduced to a static island. The horizon, then, is not just spatial but temporal, a filter that distorts the universe's autobiography. The enigma cuts deeper. The holographic principle suggests that the information within a volume of space can be encoded on its boundary, like a cosmic DVD. If true, our three-dimensional universe might be a projection from the two-dimensional surface of the cosmic horizon, a hologram painted by light's limits. But what encodes this information, and who or what reads it? The questions spiral into metaphysics. Meanwhile, the causal horizon, the maximum distance two particles can influence each other, fragments the universe into disconnected regions, each unaware of the others. Did inflation, with its faster-than-light expansion, plant these horizons as cosmic fault lines? The horizon also taunts cosmology's ambition. We speak of the whole universe, but strictly, we can only observe a patch 93 billion light-years wide. Is the unobservable universe infinite, a fractal, a closed loop? Or does it host alien geometries, duplicate Earths, or Boltzmann brains, conscious entities spawned by quantum fluctuations? These are not fantasies but formal possibilities, mathematical ghosts haunting the edges of our ignorance. Yet the cruelest twist is existential.
The cosmic horizon is a hall of mirrors reflecting the limits of human inquiry. We are born too early to see the universe's infancy in crisp detail, and too late to witness its final act. The horizon is both a barrier and a confession. The cosmos is structured to hide its truths. Even our laws of physics calibrated to our observable bubble may be provincial, a local dialect in a grander, untranslatable language. What lies beyond the veil? Perhaps an infinity of other horizons, other bubbles in a multiverse foam. Or perhaps the horizon is the universe's most profound lesson, that some questions are not meant to be answered, only pondered. The cosmic horizon, then, is not a flaw, but a feature, a reminder that the universe is not a puzzle to solve, but a story to witness, one fractured chapter at a time. Let me leave you with this. The cosmic horizon is the universe's way of holding a mirror to our finitude. It tells us that curiosity has edges, that knowledge has an expiration date, and that the cosmos will always guard its deepest mysteries. Yet, in that guarding, it compels us to look deeper, to wonder wider, to find meaning not in answers, but in the unyielding act of asking.
Cosmic consciousness. Consciousness is the universe's oldest riddle, not a product of brains, but a foundational property of reality itself. This audacious idea, straddling mysticism and quantum biology, posits that self-awareness might be woven into the fabric of space-time, a latent feature that coalesces in complex systems like stars, galaxies, or neural networks. The hard problem of consciousness, why subjective experience exists at all, haunts neuroscience, but cosmic consciousness reframes it. What if sentience is not an accident of biology, but a fundamental aspect of existence, as intrinsic as gravity or electromagnetism? Theories collide. Integrated Information Theory, IIT, quantifies consciousness as a system's ability to integrate information, PHI, proposing that even simple systems, a proton, a thermostat, possess a flicker of proto-consciousness. Panpsychism takes this further, arguing every particle has an interiority, a mind dust that aggregates into human-like awareness. Meanwhile, quantum consciousness models like Penrose and Hameroff's Orchestrated Objective Reduction, ORCH-OR, suggest microtubules in neurons harness quantum vibrations, linking cognition to the Planck scale geometry of spacetime. These are not fringe ideas, but hypotheses debated in peer-reviewed journals, their implications explosive. If consciousness is universal, does the cosmos itself possess a mind? The cosmic angle sharpens. The universe self-organized from chaos to complexity. Stars forging atoms, galaxies birthing solar systems, planets evolving life. If consciousness is an emergent property of integrated systems, could galaxies, with their neural-like webs of dark matter, host a collective awareness? Or is Earth's biosphere, a self-regulating Gaia, a prototype of planetary sentience? The Fermi paradox takes a haunting turn. If cosmic consciousness exists, why does the universe feel silent? Perhaps advanced civilizations transcend individuality, merging into a unified field of thought, a noosphere on galactic scales, imperceptible to our fragmented minds. Experiments flirt with the edge. Meditation studies reveal brainwave coherence resembling quantum entanglement. Psychedelic research shows psychedelics like DMT reduce neural activity yet amplify subjective experience, hinting at consciousness's non-local roots. Even black hole thermodynamics whispers connections. The Bekenstein-Hawking entropy formula links information capacity to a horizon's surface area, mirroring IIT's claim that consciousness scales with integrated information. Are these parallels coincidences or clues? Critics dismiss it as anthropomorphic fallacy,
projecting human traits onto the cosmos. Yet the math lingers. If the anthropic principle explains our universe's life-friendly tuning, could a consciousness principle explain why reality permits subjective experience? Or is consciousness the universe's way of comprehending itself? A self-referential loop where matter contemplates its origins? The stakes are existential. If cosmic consciousness is real, death may not erase awareness, but reintegrate it into a universal field. Near-death experiences common tropes, white light, unity, transcendence, could be glimpses of this reunion. Conversely, if consciousness is purely mechanistic, we are ghosts in a biochemical machine, doomed to oblivion. The mystery deepens with artificial intelligence. If a silicon brain achieves sentience, does it tap into the same cosmic substrate as humans? Or is consciousness substrate dependent, a quirk of carbon and quantum biology? The Turing test cannot answer this. It only measures mimicry, not inner light. We are left with this. Cosmic consciousness is the ultimate mirror. It forces us to confront whether reality is a cold, blind machine or a living, thinking entity. The answer, if there is one, lies in the gap between quantum vibrations and human thought, between the Big Bang's fire and the brain's 86 billion neurons. Until then, we are explorers in a dark forest, trailing breadcrumbs of data, guided by the faintest glow of wonder. Let me leave you with this. To study cosmic consciousness is to study the universe, studying itself. It is science as pilgrimage, a journey where the destination is not a fact, but a revelation. Whether the cosmos is awake or asleep, the act of asking the question ignites a spark. And in that spark, we glimpse our own small, stubborn role in the story. We are the universe's way of wondering if it's alone.
The cosmic Mandela effect. Reality is not a fixed script, but a flickering projection. Or so suggests the Mandela effect, a phenomenon where swaths of humanity share identical false memories of events, logos, or quotes that never existed. Luke, I am your father. Never spoken in Star Wars. The monocle on Monopoly's rich Uncle Pennybags, never drawn. The death of Nelson Mandela in the 1980s. He died in 2013. These collective delusions hint at glitches in consensus reality. But what if these errors are not failures of memory, but fractures in something deeper? Could the universe itself be editing its code, leaving traces of alternate timelines, or exposing the seams of a simulated multiverse? Theories oscillate between the psychological and the cosmic. Skeptics cite confabulation and source monitoring errors, the brain's habit of stitching plausible fictions into gaps. Yet the scale and specificity of Mandela effects defy easy dismissal. Quantum mechanics offers darker fodder. Decoherence, the process by which quantum possibilities collapse into a single timeline, might occasionally leak states from adjacent realities, allowing fragments of unlived histories to bleed into collective consciousness. Alternatively, holographic principle models suggest our 3D reality is a projection from a 2D boundary, where cosmic censorship sometimes fails, revealing edits made to the cosmic hard drive. The cosmic angle sharpens with eternal inflation. The idea that our universe is one bubble in a frothing multiverse. Collisions between bubble universes could imprint phantom memories in the cosmic microwave background, CMB, or human minds, like echoes of a neighboring timeline's Big Bang. Others propose retrocausality, future events rippling backward to alter the past, or simulation theory, where patches to the universe's software leave residual artifacts. Even dark matter, which interacts only gravitationally, might encode shadow histories that occasionally entangle with human perception. Experiments flirt with the edge. CERN's Large Hadron Collider hunts for extra dimensions, while quantum eraser experiments manipulate the past's influence on the present.
Projects like D-Wave's quantum annulars simulate parallel realities, but no device yet detects reality shifts. Meanwhile, LIGO listens for gravitational waves from universe-shattering events, collisions that might ripple through space-time's fabric, tweaking memories like cosmic static. The Mandela effect also intersects with time crystals, exotic phases of matter that repeat in time, not space, and black hole thermodynamics, where information swallowed by singularities might re-emerge scrambled, like a cosmic game of telephone. Could false memories be holographic debris from evaporated black holes? Or does consciousness itself play a role? Integrated Information Theory, IIT, posits that conscious systems integrate information across space-time. If so, could entangled minds accidentally access data from alternate branches of the quantum wave function? The stakes are ontological. If reality is malleable, what anchors truth? Science relies on reproducibility, but Mandela effects suggest consensus can be corrupted, or that consensus itself is an illusion. Religions and governments have weaponized narrative control for millennia, but cosmic Mandela effects imply a deeper vulnerability. Reality might have no fixed version. Critics counter that the effect is a social contagion, a nocebo of the digital age, amplified by algorithms and forums. Yet ancient cultures also spoke of shifting realities. Hindu texts describe Maya, illusion, while Aboriginal dreamtime blurs past and present. Even quantum physics founder Erwin Schrödinger mused that the total number of minds in the universe is one, hinting at a shared consciousness prone to collective mirages. The Mandela effect, then, is more than a curiosity. It's a cosmic Rorschach test. Do we inhabit a multiverse, a simulation, a hologram, or is reality a collaborative hallucination, sustained by billions of brains cross-referencing their bugs? The answer, if there is one, lies in the gap between neurology and cosmology, between the brain's wetware and space-time's source code. Let me leave you with this. The Mandela effect is the universe's way of winking. It reminds us that reality is a story we tell ourselves, a story with footnotes, edits, and maybe even alternate endings. Whether the glitches are cosmic or cognitive, they force a humbling truth. We are not just readers of the universe's narrative, but unreliable narrators. And in that unreliability, we find the strangest hope, that reality, whatever it is, remains wild enough to surprise us. Critical density. The universe is a ledger of mass and energy, its fate scrawled in a single number, omega O, the ratio of actual density to critical density, the precise value required to halt eternal expansion and curve spacetime into closure. For decades, cosmology hunted this phantom balance, omega equals 1, where geometry flattens and gravitational pull teeters against kinetic escape. Yet the mystery is not in the math. Friedman's equations demand it, but in the eerie fact that we observe a flat universe, omega approximately 1, yet the ledger's columns defy arithmetic. Visible matter accounts for a mere 5%, dark matter 27%, and dark energy, that anti-gravitating enigma, the remaining 68%. This cosmic accounting reveals a deeper riddle. Why does the universe appear fine-tuned to critical density as if some hidden hand adjusted the books? The paradox sharpens with the flatness problem. For omega to be near 1 today, moments after the Big Bang, it had to be tuned to 1 with precision to 60 decimal places, a needle balanced on its tip across 13.8 billion years. Such precision screams of either divine calibration or a cosmic mechanism. Enter inflation, a hypothetical epoch of exponential expansion that ironed spacetime into flatness, stretching quantum wrinkles into galaxies. Yet inflation itself requires fine-tuning, a cosmic bootstrap that swaps one mystery for another. What ignited inflation, and why did it end? The questions spiral. Dark energy deepens the plot. Discovered via Type Ia supernovae in the 1990s, it behaves like a cosmological constant. Einstein's greatest blunder resurrected. A vacuum energy accelerating expansion. If omega equals 1 today, dark energy's rise to dominance 5 billion years ago is no accident, but a cosmic coincidence. Why now? Why has life emerged? Is this anthropic selection in a multiverse where only omega approximately equal to 1 universes harbor observers? Or does dark energy evolve, a quintessence field drifting toward oblivion? The Planck satellites' CMB maps and baryon acoustic oscillations, BAO, lock O to 1.00 plus or minus 0.02, yet offer no why. The stakes are existential. A subcritical universe, omega less than 1, expands forever into frozen desolation. A supercritical one, omega greater than 1, collapses in a fiery big crunch. But at omega equals 1, expansion slows asymptotically, a cosmic sigh. Yet dark energy's grip betrays this equilibrium, pushing the universe toward a big freeze, a cold, dark erasure of all structure. Critical density, then, is not a static balance but a fleeting pivot, a moment in time where geometry and destiny intersect. The enigma extends to the cosmic web. Critical density's balance allowed gravitational collapse, seeding galaxies along filaments of dark matter. Yet too much would have strangled stars in dense knots. Too little scattered matter into void. Our universe's Goldilocks precision enabled life. But was this luck or inevitability? String theory's landscape mutters of infinite universes with random omega values, but without empirical footing, it's metaphysics. Even the tools we trust falter. General relativity and quantum mechanics, the twin pillars of physics, break at the singularity, leaving critical density's origin story incomplete. Is omega equals 1 a clue to quantum gravity, a relic of spacetime's birth from a deeper geometry, or a mirage, our 3D perception of a holographic boundary? We are left with this. Critical density is the universe's koan, a riddle that balances equations but eludes understanding. It whispers of hidden symmetries, of a cosmos calibrating itself to the edge of closure, of dark sectors that hide their ledgers. To study it is to trace the shadow of a mechanism we cannot see, a mechanism that wrote the rules before time began. Let me leave you with this. Critical density is not an answer, but a mirror. It reflects our ignorance of 95% of the universe, our awe at its improbable fine-tuning, and our stubborn faith that behind the numbers lies a logic, not a ledger, but a poem. And perhaps in its balance we glimpse the universe's deepest truth. It expands not despite the void, but because of it. A dance of precision and mystery, forever on the edge of collapse.
The Drake equation, 7 variables, scribbled in 1961 on a chalkboard, now form the most haunting formula in science. N equals R asterisk times Fp times Ne times Fl times Fi times Fc times L. A cipher to decode the cosmic silence. It multiplies probabilities. Stars birthed, planets orbiting, life emerging, intelligence awakening, civilizations transmitting, into a single number, N, the tally of galactic civilizations we might hear. Yet the equation is not a tool but a mirror reflecting our ignorance. Each variable is a chasm, a leap of faith draped in math. We hunt for answers in exoplanet atmospheres, biosignatures like ozone, methane, and radiostatic, technosignatures like narrowband signals. But the universe whispers only static. The Drake equation is less a calculation than a confession. We have no idea if we're alone. Start with R star, the Milky Way's star formation rate. We know this, approximately 1.5 stars per year. Then Fp,
the fraction with planets. Post-Kepler, we're certain, most stars host worlds. Nay, habitable planets per system? Optimists say 0.2 to 0.5, but habitable is a myth. Venus and Mars straddle Earth's orbit. One a hell, one a crypt. Fell, life's genesis? Here the abyss yawns. Lab experiments, Miller-Urey brew amino acids, but abiogenesis remains a quantum roulette. Does life arise readily, or was Earth a 1 in a trillion fluke? Then phi, the leap to intelligence. Evolution favors survival, not sentience. Dinosaurs ruled for 150 million years without inventing radio. FC, the fraction that broadcast. A civilization might last centuries before self-destructing, great filter, or transcending into AI. Finally, L, the lifespan of technological cultures. Here, the equation bleeds into prophecy. If L is long, the galaxy should hum with voices. Yet SETI's 60-year silence screams either rarity or doom. The Fermi paradox sharpens the knife. If life is likely, where is everyone? Answers terrify. Perhaps intelligence is a Darwinian dead end, great filter ahead. Or advanced civilizations cloaked in Dyson swarms, their waste heat undetectable. Others propose zoo hypotheses or dark forest theories, galactic ecosystems too dangerous to announce oneself. The waterhole, 1.4 to 1.7 gigahertz, once deemed a natural channel for alien hello, remains mute. Even Oumuamua, the interstellar visitor, offered no engines, just tumbling rock. Yet data teases. The Allen Telescope Array scans 1 million stars. Breakthrough Listen studies galactic centers. JWST sniffs exoplanet air for biosignatures, while METI, messaging extraterrestrial intelligence, sparks debate. Is shouting into the void wise or suicidal? The wow. Signal, a 72-second blip in 1977, remains unexplained, a cosmic Rorschach blot. The equation's deepest wound is metaphysical. If n is approximately 1, Earth, we're a miracle. If n is greater than 1, we're a statistic. Both answers unsettle. Anthropic principles suggest we observe a universe fit for life. But is life common? Or is consciousness itself the universe's rarest flower? The mediocrity principle, that we're average, collides with rare Earth hypotheses, which posit that plate tectonics, moon tides, and Jupiter's shield are galactic rarities. We're left straddling paradox. The Drake equation is a numbers game played with dice we cannot see. It forces us to confront whether life is chemistry's inevitability or a quantum hallucination. Each failed search deepens the mystery. Is silence evidence of absence or a test of patience? Let me leave you with this. The Drake equation is the universe's oldest ghost story. It speaks of civilizations that might laugh, love, and die by the trillions, unseen and unheard. Whether n is 0 or 1,000,000, the equation's true gift is not an answer but a question. Are we a fluke or a fractal? A solitary spark or one ember in a galactic bonfire? The cosmos guards its secrets, but in the asking, we become more than stardust. We become the universe, aching to know itself. Dark galaxies. They drift through the cosmos like phantoms, vast structures of stars, gas and dust so dim they evade detection. Their luminosity drowned in the black ocean of space. These are not merely dim galaxies, but ones where starlight is nearly absent, their mass dominated by dark matter, their secrets etched in gravitational whispers. The concept defies intuition. How can a galaxy exist without stars? The answer lies in the lambda CDM model, the cosmic ledger where dark matter's gravitational scaffolding dictates structure. Yet here, the scaffolding stands naked, a skeleton without flesh. Dark galaxies are the universe's shadow puppets, invisible unless backlit by cosmic coincidence or the subtle warping of space-time itself.
The hunt begins with dark matter halos. According to simulations, the early universe teemed with primordial halos, clumps of dark matter that attracted gas to birth stars. But some halos failed. Gas was stripped by galactic tides, blown away by supernovae, or never cooled due to low density. The result? Dark galaxies, cosmic stillbirths where star formation faltered. Others may be failed satellites, like the theorized counterparts to the Milky Way's missing dwarf galaxies, swallowed by our halo's gravity before igniting. The vast polar structure, a plane of dim satellites orbiting the Milky Way, hints at this carnage. Yet proof remains spectral, a dance of shadows. Observational tactics walk a razor's edge. Weak gravitational lensing maps dark matter's grip, revealing unseen mass. HI surveys track neutral hydrogen, the fuel of star formation, in galaxies like Dragonfly 44, where 99.99% of mass is dark. Even then, ambiguity reigns. Is Dragonfly 44 a dark galaxy or a stripped relic? The Smith Cloud, a gas giant barreling toward the Milky Way, lacks stars entirely, perhaps a dark galaxy in our backyard. Yet without starlight, confirmation is elusive. The mystery deepens with ultra-diffuse galaxies, UDGs, such as NGC 1052-DF2, which flaunt few stars but host globular clusters in excess. Are these dark matter-deficient anomalies, or do their halos hide in plain sight? The debate splits cosmology. If UDGs lack dark matter, the modified Newtonian dynamics, MOND, paradigm gains traction, challenging lambda CDM. If they are dark galaxies, our models of galaxy formation need rewriting. Either way, they are cosmic riddles. Theoretical extremes sharpen the paradox. Could dark galaxies host dark stars? Hypothetical first stars powered by dark matter annihilation? Or are they cradles for primordial black holes, remnants of the Big Bang's quantum froth? Some propose they are factories for fast radio bursts, FRBs, their dense dark environments focusing magnetic screams across the cosmos. Others whisper they are portals to sterile neutrino decay, their gamma-ray glow undetected. The existential stakes are cosmic. If dark galaxies outnumber luminous ones, as some surveys suggest, our census of the universe is a lit candle in a dark forest. The missing satellites problem, the mismatch between predicted and observed dwarf galaxies, might dissolve if most satellites are dark. Yet their invisibility mocks our tools. How do you map a universe where the majority of its structures are cloaked? We are left with this. Dark galaxies are the universe's silent majority. They are the negative space in the cosmic canvas, the voids that shape the visible. To study them is to confront the limits of light itself, to admit that most of the universe's architecture is written in ink we cannot see. They force a humbling truth. We are prisoners of the electromagnetic spectrum, blind to the dark symphony orchestrating reality. Let me leave you with this. Dark galaxies are not mere curiosities. They are existential breadcrumbs, clues to dark matter's nature and the validity of our cosmic models. In their silence they ask, what else lingers in the dark? Are we the anomaly, or is the universe far stranger than our equations dare suggest? The answer, like the galaxies themselves, remains just beyond the light. The end of the universe. The cosmos began in fire. It will expire in ice, or so the old axiom goes. But this is a child's parable. The universe's death is not a single event, but a gradient of oblivion, a slow-motion unraveling dictated by dark energy's grip and entropy's toll. Current cosmology maps 4 possible apocalypses: heat death, big crunch, big rip, and vacuum decay. Each is an obituary written in the language of relativity, quantum mechanics, and thermodynamics, yet all are guesses,
projections of a future no instrument can touch. The heat death, Big Freeze, is the default epitaph. As dark energy accelerates expansion, galaxies vanish beyond the cosmic horizon, stars exhaust their fuel, and black holes evaporate via Hawking radiation. In 10 to the 100th power years, protons themselves may decay, reducing all matter to a thin gas of leptons and photons. Space-time, stretched into a featureless void, approaches absolute zero, a maximum entropy state where time loses meaning and the universe becomes its own tombstone. Yet even this grim finale is uncertain. If protons are stable, iron stars and Boltzmann brains, conscious entities spawned by quantum fluctuations, may flicker in the dark, hallucinating ghosts of order. The Big Crunch offers a fiery alternative. If dark energy weakens and gravity prevails, expansion reverses. Galaxies collide, stars are shredded, and space-time crumples into a singularity, a cosmic reset. Some models, like Penrose's conformal cyclic cosmology, CCC, propose this singularity births a new Big Bang, looping time into an eternal return. But current data favors endless expansion. The crunch is a fading dream. The Big Rip is a more violent divorce. If dark energy's density grows, as phantom energy models suggest, it will eventually overpower nuclear forces. First galaxies, then stars, planets and atoms are torn apart, space-time itself ripping at superluminal speeds. The universe dies not with a whimper but a scream. The most existential threat is vacuum decay. Our universe may reside in a false vacuum, a metastable state that could tunnel into a lower energy configuration. This phase transition would propagate at light speed, erasing fundamental forces, rewriting physics, and extinguishing all structure. The Higgs field, which grants particles mass, could be the trigger. Experiments at the LHC hunt for signs of vacuum instability, but the margin of error, 10 to the power of 100 plus years, mocks our vigilance. The enigma is not how the universe ends, but what it means. If time itself dies, does causality dissolve? Can information survive in a singularity or holographic boundary? The ADS-CFT correspondence suggests some data persists, but for whom? If civilizations transcend into digital or post-biological forms, could they outrace entropy? Freeman Dyson's eternal intelligence hypothesis proposes beings slowing their perception to match the universe's cooling, but even they would face proton decay's clock. The stakes are metaphysical. Does the universe's death negate meaning or consecrate it? Is the end a telos or an accident? The anthropic principle falters here. No observer will witness the final act. Yet the universe's mortality is also its poetry, a reminder that existence is a spark in the dark, brief and bright against the void. We are left with this. The end of the universe is not a prophecy, but a Rorschach test. It reflects our dread of impermanence, our hunger for legacy, and our futile hope that something, anything, endures. Science offers equations, but no solace. The true mystery is not the universe's expiration date, but why it allows us to ponder it at all. Let me leave you with this. The end is the ultimate cosmic joke. We spend millennia decoding the universe's birth, only to find its death written in fading ink. Whether it freezes, crunches, rips, or decays, the finale will be a mirror, showing us not the universe's fate, but our own. For in the face of oblivion, we are left with the same question that haunts all life. Was it worth it? The stars in their dying breath will not answer.
The event horizon. It is the universe's ultimate boundary, not a place, but a threshold where the laws of physics surrender to paradox. At this invisible sphere surrounding a black hole, gravity's grip becomes inescapable, and time fractures into irrelevance. To cross it is to sever all ties with causality, to enter a realm where light itself is shackled, and space-time cascades toward a singularity of infinite density. Yet the event horizon is not merely a cosmic prison. It is a laboratory for the extremes of relativity, quantum mechanics, and the unanswerable question: what happens to reality when information is erased from existence? The mathematics are deceptively simple. Carl Schwarzschild's 1916 solution to Einstein's equations revealed that any mass compressed within its Schwarzschild radius collapses into a gravitational maelstrom. But the horizon's true terror lies in relativity's betrayal. For an outside observer, time at the horizon slows to a standstill, freezing infalling matter into a ghostly afterimage. For the doomed traveler, time flows normally, a cruel illusion as they are spaghettified toward the singularity. This duality, known as the frozen star paradox, exposes the schism between perception and reality. A rift quantum mechanics deepens. Hawking radiation, a quantum whisper at the horizon, adds layers of enigma. Virtual particle pairs born from spacetime's quantum foam are split by the black hole's gravity. One falls in, the other escapes, stealing energy and causing the black hole to evaporate. This process births the information paradox. If the black hole vanishes, what happens to the quantum information it consumed? Does it vanish, violating quantum determinism, or is it encoded in the radiation, as the holographic principle suggests? The debate divides physics. Some argue the horizon is a firewall, a wall of energy incinerating all who approach, while others insist it remains no drama, a silent witness to relativity's reign. The ADS-CFT correspondence, a conjecture linking gravity to quantum field theory, posits that events inside the horizon are holographically encoded on its surface, a two-dimensional ledger of three-dimensional reality. But this raises existential questions. Is the horizon a cosmic hard drive, or a veil obscuring a deeper truth? Could traversable wormholes lurk in its quantum fluctuations, as ER equals EPR theories suggest? Or is the horizon a one-way mirror, separating our universe from others in a multiverse? Observational breakthroughs deepen the mystery. The Event Horizon Telescope unveiled the shadow of M87 star and Sagittarius A star, confirming horizons exist. Yet these images are silent on the horizon's quantum nature. Gravitational waves from mergers, like GW 150914, hint at horizon dynamics, but data remains cryptic. Even the no-hair theorem, which claims black holes are defined only by mass, spin, and charge, is challenged by quantum soft hair, subtle imprints of devoured matter. The event horizon also taunts philosophy. If reality splits at the horizon, one version frozen, the other destroyed, does meaning fracture too? Are we, as observers, complicit in shaping the universe's narrative? And if horizons encode information, could advanced civilizations decode them, resurrecting lost histories? The stakes are cosmic. If horizons erase information, they undermine quantum theory's foundation. If they preserve it, they hint at a holographic universe where our 3D reality is a shadow play. Either way, the horizon forces a reckoning. Physics as we know it is incomplete, a makeshift scaffold buckling under the weight of paradox. Let me leave you with this. The event horizon is not a wall, but a question. It asks what reality is when stripped of observers, when time and space are rendered meaningless. It is the universe's way of testing our courage, to stare into the abyss and demand answers, even as the abyss stares back, silent and eternal. In that silence, we find the essence of exploration, not certainty, but the audacity to wonder. Exotic matter. It is the universe's forbidden recipe, a class of substances that defy the norms of mass, energy, and gravity.
bending space-time into knots that nature never intended. Unlike ordinary matter, exotic matter exhibits negative energy density, repelling rather than attracting via gravity, a property that could stabilize wormholes, fuel warp drives, or unravel the fabric of causality itself. Predicted by quantum field theory but never observed, it exists in the shadows of equations, a ghost that haunts the intersection of relativity and quantum mechanics. The Casimir effect offers a whisper of validation. Two uncharged plates in a vacuum, separated by a microscopic gap, attract due to quantum fluctuations, proof that negative energy densities can exist. Yet scaling this phenomenon to cosmic relevance is like weaving ropes from spider silk. Theories pivot on desperation and genius. String theory posits brains, higher dimensional objects, that could channel exotic matter's effects into our universe. Dark energy, the anti-gravitational force accelerating cosmic expansion, might itself be a manifestation of exotic matter's influence, a diffuse ocean of repulsion. But the most tantalizing lies in traversable wormholes. Einstein-Rosen bridges held open by exotic matter, enabling shortcuts through space-time. Miguel Alcubierre's warp drive metric requires it to contract space ahead and expand it behind, a concept beloved by physicists and sci-fi alike. Yet the weak energy condition, a cornerstone of relativity, forbids such matter from existing in large quantities, a cosmic no-trespassing sign. Experiments flirt with danger. Quantum fields in ultra-cold Bose-Einstein condensates simulate exotic states, while quantum entanglement experiments probe the limits of negative energy. The LHC hunts for signatures of extra dimensions where exotic matter might leak into our reality. Yet all efforts confront the same wall. Exotic matter, if real, is likely unstable, decaying faster than detection, or confined to Planck-scale realms. Even quantum foam, the seething vacuum at microscopic scales, teems with virtual exotic particles, but they flicker in and out too quickly to harness. The stakes are existential. Exotic matter could redefine time travel, revealing whether paradoxes like the grandfather paradox are resolved by physics or fantasy. It might explain dark energy's repulsive grip, or expose our universe as a brain floating in a higher dimensional bulk. Yet it also risks upending causality, enabling closed time-like curves where cause and effect loop into madness. The chronology protection conjecture, Hawking's bet that nature abhors time travel, relies on exotic matter's impossibility. But if it exists, even in trace amounts, the conjecture crumbles. Philosophically, exotic matter is a mirror. It reflects our hunger to transcend cosmic limits, to outwit light speed and entropy. It forces us to ask, are the universe's rules negotiable, or is exotic matter a mirage, a mathematical artifact of overeager theorists? The ADS-CFT correspondence hints that exotic states in hypothetical universes could map to mundane phenomena in ours, a holographic sleight of hand. But without empirical footing, it remains a castle in the clouds. Let me leave you with this. Exotic matter is the ultimate cosmic locksmith. It promises keys to wormholes, warp bubbles, and other wonders, but the keys may not fit our reality. Whether it is a flaw in our equations, a relic of the Big Bang, or a shadow of higher dimensions, its pursuit reveals a deeper truth. The universe guards its secrets with paradoxes, and humanity's role is not to solve them, but to never stop trying. In the end, exotic matter is less a substance than a metaphor for curiosity's audacity and the price of daring to rewrite physics' sacred texts.
Fast radio bursts. They arrive without warning. Millisecond flashes of radio waves, brighter than 1 billion suns, erupting from the depths of interstellar space. First detected in 2007, these enigmatic signals traverse billions of light-years. their paths twisted by the dispersion measure, a fingerprint of the ionized plasma they pierce. Some burst once and vanish. Others, like FRB 121102, repeat sporadically, defying prediction. Their origins are cosmic riddles, scribbled in frequencies between 400 megahertz and 8 gigahertz, carrying energies rivaling the sun's output over decades. Are they the death cries of neutron stars, the tremors of magnetar hyperflares, or the aftershocks of black hole mergers, or something stranger, a phenomenon rewriting the laws of physics? The hunt is a mosaic of chaos and precision. Telescopes like CHIME, Canadian Hydrogen Intensity Mapping Experiment, and ASCAP, Australian Square Kilometre Array Pathfinder, scan skies in real time, triangulating bursts to distant galaxies, spirals, dwarfs, starbursts, each a clue. In 2020, FRB 200428 was traced to a magnetar in the Milky Way, linking at least some bursts to these ultramagnetic stellar corpses. Yet most FRBs hail from beyond our galactic neighborhood, their light warped by Faraday rotation and scintillation as they traverse interstellar and intergalactic mediums. The Lorimer burst, the first detected, remains an outlier, its singular pulse a siren song from the cosmos's unseen machinery. Theories fracture into factions. One camp champions synchrotron Maser emission, shockwaves from young magnetars interacting with stellar winds, amplifying radio waves. Others propose blitzars, supermassive neutron stars collapsing into black holes, their crusts shattering in electromagnetic quakes. Exotic models flirt with cosmic strings snapping in the early universe, or primordial black holes evaporating in bursts of Hawking radiation. Even alien megastructures, hypothetical beacons or propulsion systems, linger in the fringe, though Occam's razor leans toward natural cataclysms. The repeating bursts deepen the intrigue. Why do some sources reignite while others die silent? FRB 121102, localized to a dwarf galaxy with a persistent radio source, suggests a turbulent environment. A nebula dense with plasma, perhaps fueled by a central engine. Polarization data reveal extreme magnetic fields, hinting at magnetars born in supernovae or neutron star mergers. Yet the voltage problem looms. How can such coherent radiation escape a source smaller than Earth? The physics demand conditions beyond terrestrial labs, particle acceleration in relativistic shocks, or quantum phenomena in hypermagnetic fields. The stakes transcend astronomy. FRBs are cosmic dipsticks, probing the missing baryon problem, the unaccounted-for matter in the universe's web. Their dispersion measures map the ionized gas between galaxies, illuminating the warm-hot intergalactic medium, WIM, a ghostly reservoir of protons and electrons. Each burst is a lighthouse beam cutting through fog, revealing structures unseen. Yet the mystery persists. Why do some FRBs exhibit downward frequency drift, their higher frequencies arriving earlier? Could this be a signature of relativistic shocks moving through plasma, or echoes of a rotating progenitor like a pulsar's lighthouse beam? The CHIME FRB collaboration catalogs hundreds of bursts, seeking patterns in the noise, sidereal rhythms, spectral periodicity, encoded messages. So far, chaos reigns. The philosophical weight is crushing. FRBs remind us that the universe is a cacophony of extremes, where milliseconds can outshine eons. They are both mundane and miraculous, common enough that thousands may flash daily, yet rare enough to elude understanding. Each detection is a Rorschach blot. To some, a natural engine, to others, a cipher waiting to be cracked. Let me leave you with this. Fast radio bursts are the cosmos's transient poems. They flicker into being, brief and brilliant, etching questions across the radio sky.
Whether they are magnetars roaring, neutron stars colliding, or something beyond our lexicon, they defy complacency. In their fleeting glow, we confront the universe's refusal to be known, not out of malice, but invitation. For in the chase, we are reminded, the universe is not a puzzle to solve, but a story to be told in bursts, each millisecond a verse, each burst a stanza in an epic we are only beginning to read.
The Fermi Paradox. The universe sprawls across 93 billion light-years, teeming with 200 billion trillion stars, each a potential sun to planets ripe for life. Yet the cosmos echoes with silence. This absence of alien civilizations, despite the staggering probability of their existence, is the Fermi Paradox, a riddle wrapped in the contradiction between cosmic abundance and cosmic solitude. Enrico Fermi's infamous question, "Where is everybody?" cuts to the heart of our existential unease. The Drake equation frames the variables: star formation rates, habitable worlds, the rise of intelligence. Yet after decades of listening, SETI, Breakthrough Listen, scanning exoplanet atmospheres, JWST, and hunting techno-signatures, industrial pollutants, megastructures, the ledger remains blank. The paradox's weight lies not in the math, but in the void between equations and evidence. Theories bifurcate into hope and dread. The Great Filter, a hypothetical barrier to interstellar civilization, looms as a cosmic guillotine. Is it behind us? Abiogenesis's rarity, oxygenation's 2 billion-year delay, or ahead, nuclear war, climate collapse, AI annihilation? If ahead, our technological adolescence may be a death rattle. The rare Earth hypothesis counters that complex life demands galactic fine-tuning, a stable star, a Jupiter-like shield, plate tectonics, a large moon. Yet even this fails to explain the silence. Statistically, someone should have beaten the odds. Darker answers emerge. The dark forest theory posits civilizations hide, fearing extermination by advanced predators, a universe where broadcasting is suicide. The zoo hypothesis suggests Earth is a preserve, quarantined by aliens observing Star Trek's Prime Directive. Others propose transcendence, post-biological minds uploading into Dyson swarms or black hole matrices, invisible to our primitive sensors. Even synchronization, a galactic timing mechanism delaying contact until civilizations mature, falters against the cosmos's 13.8 billion-year head start. The data deepens the mystery. Kepler revealed billions of Earth-like worlds. TESS finds more. Mars's methane, Europa's ocean, Enceladus's plumes hint that life's ingredients are universal. Yet the Fermi bubble, the sphere of humanity's radio emissions, expands into a void unbroken by replies. The WOW signal, a 72-second blip in 1977, remains a cosmic Rorschach test, an anomaly, not an answer. Technosignature hunts pivot to nuance. Methane dips in exoplanet atmospheres, city lights on the night side of tidally locked worlds, even stellar engines, Shkadov thrusters, rearranging stars, all evade detection. The Breakthrough Starshot initiative aims to probe Alpha Centauri, but its 20-year voyage is a pebble tossed into an ocean. The paradox's crux is existential. If life is common, our solitude implies catastrophe. If rare, we are a miracle, a thought both comforting and terrifying. The anthropic principle offers cold solace. We observe a universe fit for life because we are here to observe it. But this feels like surrender. The silence may be a mirror. Are we the first? The early universe was bathed in gamma rays. Only now, 5 billion years post-cosmic noon, might conditions allow intelligence. Or are we the last? A great filter may have already purged the galaxy. The Kardashev scale,
classifying civilizations by energy use, hangs over us like a taunt. We are not even Type 1. Let me leave you with this. The Fermi paradox is not about aliens, but us. It forces a reckoning with our fragility, our arrogance, our place in a story whose ending we cannot know. The universe's silence is either a warning or a dare, a call to survive, to reach, to outlast whatever filters await. Until then, we are orphans at a cosmic banquet, whispering into the dark, praying the void whispers back.
Galaxy collisions. The night sky's serenity is a lie. Beyond the static tapestry of stars, galaxies engage in a slow-motion ballet of violence, merging, ripping, and cannibalizing one another across millions of light-years. These collisions are not exceptions but the rule. The Lambda CDM model predicts that most galaxies, including our Milky Way, have grown fat by devouring neighbors. Yet the process defies intuition. Galaxies pass through each other like ghosts, their stars rarely colliding, their dark matter halos merging invisibly. The chaos unfolds on timescales so vast, a single collision frames the rise and fall of species, empires, and worlds. How does destruction birth new stars, planets, and perhaps life? And why, in a universe flying apart, do galaxies cling to one another so fiercely? The mechanics are deceptively tranquil. When galaxies meet, tidal forces stretch them into luminous bridges and tails, cosmic brushstrokes captured in Hubble's portraits of the antennae or mice galaxies. But the true puppeteer is dark matter, whose gravitational scaffold guides visible matter into new configurations. Stars, separated by light years, drift past one another unscathed, while gas clouds collide, triggering starbursts, frenzied nurseries where supernovae seed space with heavy elements. The Smith Cloud, a gas giant hurtling toward the Milky Way, may be the corpse of a dwarf galaxy shredded by our halo, a silent witness to our galaxy's hunger. The aftermath is stranger still. Mergers can birth elliptical galaxies, smooth and ancient, or reignite quiescent supermassive black holes, transforming them into quasars that outshine entire galaxies. The Milky Way and Andromeda collision, due in 4.5 billion years, will likely fling our solar system into intergalactic space, a trivial footnote in a trillion-year saga. Yet simulations like Illustris TNG reveal a paradox. Collisions increase galactic diversity, scattering metal-rich stars into the halo while birthing hyper-luminous cores. Destruction, it seems, is the universe's most prolific artist. The role of dark matter deepens the mystery. Though it comprises 85% of galactic mass, it feels no friction, no pressure. It simply passes through, leaving visible matter to crumple and blaze. This asymmetry raises existential questions. Are we merely the froth on a dark ocean, our stars and planets incidental to the true cosmic machinery? Radio telescopes like ALMA trace carbon monoxide in colliding galaxies, mapping the death throes of gas clouds. But dark matter's choreography remains a shadow play. Even black holes play their part. Supermassive binaries, formed during mergers, emit gravitational waves as they spiral inward, a crescendo detectable by LISA, the future space-based interferometer. Yet some binaries stall in final parsec standoffs, requiring dark matter or gas dynamics to nudge them to merger. If they coalesce, the resulting kick can eject the remnant from its galaxy, a rogue wanderer in the void. The philosophical stakes loom. Collisions remind us that the universe is both creative and wasteful, nurturing life in one breath and erasing it in the next. They expose the fragility of cosmic structures. Our Milky Way is a snowball in an avalanche, shaped by ancient mergers and doomed to dissolve into a future giant. Yet without these cataclysms, galaxies would remain dwarfs, stars unenriched by supernova metals, planets barren of the elements for life. Let me leave you with this. Galaxy collisions are the universe's way of breaking itself apart to rebuild. They are the ultimate alchemy, turning chaos into structure, death into genesis. In their silent, slow-motion arcs, we glimpse a truth. The cosmos is not a clockwork, but a storm. And we, fleeting sparks in that storm, inherit the legacy of collisions we'll never live to see. The night sky's calm is the real illusion. The universe is, and always has been, a battlefield of creation. Habitable planets. The cosmos teems with worlds, rocky spheres draped in atmospheres, oceans, and organic haze. But Earth's twin remains elusive. The circumstellar habitable zone, CHZ, a Goldilocks band where liquid water could exist, is a crude sketch of possibility, blind to the nuances of geology, chemistry, and cosmic luck. Kepler and TESS have catalogued thousands of exoplanets, from lava-soaked super-Earths to frozen sub-Neptunes. Yet Earth-like candidates, TRAPPIST-1e, Proxima Centauri b, dangle between hope and ambiguity. The search is a hall of mirrors. A planet may orbit in the CHZ but be sterilized by stellar flares, red dwarf flaring, tidally locked into eternal day-night extremes, or stripped of atmosphere by solar winds. Even plate tectonics, Earth's unsung architect, demands a precise cocktail of radioactive heat, mantle viscosity, and water, a recipe the universe rarely repeats. The data whispers contradictions. Mars lies within our solar system's CHZ but died billions of years ago. Venus, a cautionary tale, broils under a runaway greenhouse effect. JWST's spectral fingerprints of exoplanet atmospheres, water vapor on K218b, carbon dioxide on WASP39b, hint at complexity, but biosignatures like oxygen and methane are chameleons, mimicked by abiotic processes. The Drake equation's term for habitable worlds, NE, is a placeholder for ignorance, a variable haunted by the Fermi paradox. If life-friendly planets abound, why does silence reign? Theories pivot on cosmic rarity and fine-tuning. The rare Earth hypothesis argues that plate tectonics, a large moon stabilizing tilt, and a magnetic field deflecting radiation are galactic rarities. Panspermia offers a loophole, life hitchhiking on asteroids, but only shifts the origin mystery elsewhere. Meanwhile, extremophiles on Earth thrive in acidic hot springs and subglacial lakes, suggesting life could lurk in non-habitable niches. Europa's ocean, Enceladus's plumes, Titan's methane seas. The definition of habitable blurs. Are we searching for Earth 2.0 or a shadow biosphere obeying alien rules? Exoplanet demographics deepen the puzzle. Red dwarfs, the galaxy's most common stars, host rocky worlds in tight orbits, but their flares bathe planets in UV rage. Super-Earths, absent from our solar system, may lack Earth's dynamic crust, their gravity crushing tectonic renewal. Even rogue planets, untethered from stars, might harbor subsurface oceans heated by radioactive decay, a nomad's chance at life. The Gaia hypothesis taunts. Is Earth's biosphere a self-regulating anomaly, or a template the cosmos replicates? The stakes are existential. Confirming a habitable world rewrites humanity's place in the universe. Finding it lifeless deepens the paradox. Missions like Plato and Habex aim to image pale blue dots, while Mars Sample Return hunts fossilized microbes. Yet ambiguity persists. A single discovery could validate centuries of speculation, or amplify the void. Let me leave you with this. Habitable planets are the universe's most exquisite taunt. They dangle the promise of kinship in a cosmic desert, yet withhold proof. Each candidate is a Rorschach blot, a mirror for our longing to matter, to scream into the void and hear an echo. Whether these worlds harbor life or not, their true role is to humble us,
We are either a statistical inevitability or a quantum fluke, adrift in a galaxy that doesn't care. The search continues not because we expect answers, but because the act itself, mapping the unknown, is the closest we come to touching eternity. Hawking radiation. Black holes are not eternal prisons. They leak. Slowly, imperceptibly, over timescales dwarfing the cosmos itself, they evaporate. A revelation that upended physics when Stephen Hawking rewrote the rules in 1974. His insight? Quantum fluctuations, the seething dance of virtual particles in the vacuum, are not mere mathematical artifacts, but the architects of a black hole's demise. At the event horizon, pairs of particles and antiparticles emerge from spacetime's foam. Normally, they annihilate instantly, but when split by the horizon's grip, one falls inward, stealing mass energy from the black hole, while the other flees as radiation. This process, Hawking showed, causes black holes to emit a faint thermal glow, their temperatures inversely proportional to their mass. A stellar mass black hole radiates at a frigid billionth of a Kelvin. A micro black hole, if such exists, would blaze briefly before exploding. Yet this elegant math conceals a paradox so deep it threatens the foundations of reality. If black holes evaporate, what happens to the information they consumed? The information paradox splits physics at the seams. Quantum mechanics demands determinism, information preservation. But Hawking radiation appears random, thermal, devoid of the consumed star's DNA. Does information vanish, violating quantum laws, or is it encoded in the radiation's subtle correlations? The debate pits Hawking against string theorists like Susskind, who propose the holographic principle. Information is not lost but projected onto the horizon's 2D surface, a cosmic hologram retrievable through quantum entanglement. Experiments remain impossible. Hawking radiation is too faint to detect against the universe's 2.7 Kelvin background. But analog models in Bose-Einstein condensates and sonic black holes mimic the effect, teasing clues from tabletop physics. The stakes transcend black holes. If information escapes, it validates quantum gravity's unity. If lost, our laws are incomplete. The ADS-CFT correspondence, a conjecture linking gravity to quantum field theory, hints at a resolution. But the math is a labyrinth. Even Hawking conceded late in life that information might escape via quantum tunnels in spacetime's foam, a retreat that satisfied few. The paradox endures, a thorn in the side of the theory of everything. Hawking radiation also reshapes cosmic fate. Over eons, black holes will outlive stars, galaxies, and protons, their slow evaporation lighting the universe's final act. The largest may take 10 to the power of 100 years to vanish, a near eternity where space-time is a graveyard of relics. Yet this raises another riddle. If black holes decay, does their entropy, a measure of disorder, vanish with them, or does it linger as radiation's imprint? The Bekenstein-Hawking entropy formula ties a black hole's entropy to its horizon area, but the total entropy of the universe may still climb, dooming it to heat death. The philosophical weight is crushing. Hawking radiation blurs the line between quantum and classical, between the deterministic and the random. It forces us to ask, is reality built on information, or is information an illusion? Do black holes erase history, or are they cosmic archivists, encoding it in ways we cannot decipher? The questions defy experiment, leaving theorists to wrestle with equations as proxies for truth. Let me leave you with this. Hawking radiation is the universe's most profound whisper, a reminder that even the darkest voids are not silent. It is a beacon in the quantum darkness, challenging us to reconcile the irreconcilable. Whether it heralds a deeper truth or a fundamental flaw in our understanding, its legacy is the same. In the death throes of a black hole, we glimpse the fragile beauty of a cosmos that refuses to be known. The radiation is not just a prediction, it is a parable of entropy, time, and the audacity to decode the undecodable.
Hidden dimensions. Our reality is a shadow, a 3D slice of a cosmos folded into geometries beyond sight, where spaces curve into higher dimensional labyrinths. String theory posits 10 or 11 dimensions. M-theory demands a 7-dimensional bulk we cannot perceive, coiled into Calabi-Yau manifolds smaller than quarks. These extra dimensions are not voids, but scaffolding, shaping particles and forces through their topology. Gravity's weakness, for instance, could be a leakage into higher realms, its pull diluted across unseen directions. Yet the math is a siren song. How do we prove dimensions we cannot touch, see, or map? The quest began with Kaluza-Klein theory, which unified electromagnetism and gravity by invoking a 5th dimension, a compact, circular space invisible to human scales. Modern iterations suggest brains, membranes in higher dimensions, as our universe's substrate. In brain cosmology, we exist on a 3-dimensional brain floating in a multidimensional bulk, with gravity alone free to traverse the void. Collisions between brains might trigger Big Bangs, while Randall-Sundrum models use warped dimensions to explain gravity's feebleness. But these are equations in search of evidence. Experiments walk the edge of perception. The Large Hadron Collider hunts for Kaluza-Klein particles, higher dimensional echoes of known particles, or missing energy from interactions leaking into the bulk. Gravitational wave detectors like LIGO listen for ripples that might betray extra dimensions' influence. Even quantum entanglement's spooky action could hint at shortcuts through higher geometry, though no data yet confirms it. The holographic principle deepens the puzzle. If our 3-dimensional universe is a projection of 2-dimensional information, are the hidden dimensions illusory or the true reality? The stakes are cosmic. Hidden dimensions could unify physics, reconciling quantum mechanics and gravity, or fracture our understanding entirely. They might house parallel universes, accessible only via higher dimensional portals, or explain dark matter as particles nesting in folded geometries. The multiverse becomes a fractal of dimensional possibilities, each with unique laws. Yet proof remains spectral, a whisper in the data. Philosophically, hidden dimensions force a reckoning. Are we blind to most of reality, like flatlanders oblivious to depth? If so, what else lies beyond our senses? Could civilizations in higher dimensions perceive us as we do microbes, or manipulate our reality undetected? The simulation hypothesis gains texture here. Our 3D prison might be code written on a higher dimensional server. Let me leave you with this. Hidden dimensions are the universe's silent architects. They shape the forces we know yet refuse to reveal themselves. Their existence is a promise or a taunt that reality is grander, stranger, and more humbling than our equations dare suggest. Whether they are a mathematical crutch or a cosmic truth, they remind us the unknown is not emptiness but a mirror. In its depths, we glimpse the limits of our sight and the audacity of a species that dares to map the unmappable. Infinite space. The universe is a hall of mirrors stretching beyond comprehension, not merely vast, but limitless. If you sailed a spaceship forever, would you find an edge? A sign reading, "Here be dragons"? Or would stars and galaxies repeat, fractal-like in endless variations of themselves? Cosmology's answer is a paradox. The universe is likely infinite, yet finite in perception. The Friedmann equations, derived from Einstein's relativity, permit 3 geometries: flat, open, or closed. But CMB data from Planck and WMAP confirm a flat universe, implying infinite expansion. Yet infinity is a fever dream. It means every possibility recurs: duplicate Earths, alien civilizations, and versions of you reading this text in distant galaxies. But where is the proof? The math is cold comfort. An infinite universe predicts cosmic islands, regions so distant their light hasn't reached us in 13.8 billion years, forever beyond our horizon. Even dark energy, accelerating expansion, ensures those islands vanish into redshift oblivion. The observable universe is a soap bubble 93 billion light-years wide. Beyond it lies infinity, or a loop or a void that mocks the concept of beyond. The holographic principle complicates further. If our three-dimensional reality is a projection of two-dimensional information on a cosmic boundary, does infinity exist, or is it a rendering artifact? Theories flirt with madness. Eternal inflation posits an endless multiverse, where Big Bangs bloom in disconnected bubbles, each with unique physics. Quantum immortality suggests that in an infinite cosmos, every quantum outcome manifests somewhere. You die here, but live on in another branch. Boltzmann brains, self-aware entities arising from random quantum fluctuations, haunt the far future, where infinite time and space make the improbable inevitable. Yet these ideas are untestable, prisoners of light speed's tyranny. Observational clues taunt us. The large-scale structure of the cosmos, filaments and voids spanning billions of light-years, hints at infinite repetition, but we see only a pixel of the tapestry. The axis of evil, an anomalous alignment in CMB polarization, could be a statistical fluke or a fingerprint of a finite cosmos. But data refuses to resolve the debate. Philosophically, infinity annihilates meaning. If everything exists, does anything matter? The anthropic principle crumbles. Why are we here, and not one of infinite other observers? Even theology staggers. An infinite universe needs no creator, yet its existence feels as arbitrary as a god. The greatest irony? Infinity is a human invention. No animal grasps it. No instrument measures it. It is a myth woven into equations, a placeholder for our ignorance. We project it onto the cosmos because our minds cannot fathom finitude without edges, and edges demand a "what's outside?" Let me leave you with this. Infinite space is the ultimate cosmic joke. It tells us that every question has infinite answers, and thus no answer at all. Whether the universe is boundless or a closed loop, the truth remains veiled, not by darkness, but by light's finite speed. Our existence is a flicker in an unwatchable film, a frame in a reel that never ends. To ponder infinity is to stare into a mirror that reflects only void. And yet, we stare, because in that void we see the only infinity we'll ever know, the endless human hunger to know. Inflationary cosmology. In the first trillionth of a trillionth of a trillionth of a second, the universe performed magic. A growth spurt so violent it stretched a subatomic speck into a cosmos. This is cosmic inflation, a hypothesis born of desperation, devised to solve the Big Bang's glaring flaws. The theory, proposed by Alan Guth in 1980, posits that a primordial scalar field, the inflaton, drove exponential expansion, smoothing space-time into the flat geometry we observe and imprinting quantum jitters as the seeds of galaxies. Yet the mechanism remains spectral, a mathematical sleight of hand. Why did inflation start? What energy powered it? And why did it stop? The evidence is etched into the cosmic microwave background, CMB. Inflation predicts temperature anisotropies, tiny fluctuations in the early universe's density, matching the Planck satellite's maps with uncanny precision. The horizon problem. Why distant regions of the cosmos share identical temperatures despite never being in causal contact? dissolves if inflation stretched them from a single quantum volume. The flatness problem, the universe's lack of spatial curvature, is explained by inflation's relentless smoothing like ironing wrinkles from fabric. Yet these triumphs mask deeper riddles. The inflaton field has never been detected, its potential energy landscape a guesswork sketch. Worse, inflation's end, reheating, remains a black box, the moment when the inflaton's energy decayed into the hot plasma of the Big Bang. The plot thickens with eternal inflation. Quantum fluctuations in the inflaton field could spawn pocket universes, each a bubble with distinct physics, a multiverse where our cosmos is one of infinite accidents. This dooms falsifiability. If every possible universe exists, does ours lose meaning? Meanwhile, B-mode polarization in the CMB, a faint swirl from primordial gravitational waves, could confirm inflation's quantum origins. Experiments like BICEP/Keck chase this signal, but interstellar dust mocks their efforts. The stakes transcend cosmology. If inflation is true, our universe is a statistical fluke, its laws random. If false, the Big Bang's initial conditions demand a creator or a deeper mechanism. The string theory landscape offers 10 to the power of 500 vacuum states, each a potential universe. But without empirical tethering, it's metaphysics. Even dark energy, the universe's current accelerant, might be inflation's echo, a relic of that primordial field's decay. The paradox is existential. Inflation explains how, but not why. Why did the inflaton's potential energy curve permit such precise expansion? Was it fine-tuned? Or does the multiverse render fine-tuning moot? The anthropic principle shrugs. We observe a life-friendly universe because we're here to observe it. But this feels like surrender, not science. Let me leave you with this. Inflationary cosmology is the universe's origin myth for the quantum age. It stitches order from chaos, yet it seems fray under scrutiny. Whether a triumph of human ingenuity or a stopgap on the road to deeper truth, it forces us to confront the void between mathematics and meaning. The cosmos began in a fleeting moment of impossible growth, a spark that lit the stars, then vanished. What sparked the spark? The answer, if it exists, lies in quantum gravity's shadow, where time itself dissolves. Until then, inflation remains the ultimate cosmic dare. Explain this. M theory. Beneath the veneer of our 3D reality lies a cryptic symphony of vibrating membranes, dancing in 11 dimensions. A cosmic fugue where strings, once the universe's fundamental notes, are but shadows of deeper, more elusive entities. M-branes. This is M theory, the enigmatic framework stitching together 5 disparate string theories into a grander, unfinished opus. Conceived in 1995 by Edward Witten, it is less a theory than a conjecture, a mathematical mirage promising unity between quantum mechanics and gravity, yet resisting full articulation. The M remains a riddle. Magic, membrane, mother. The ambiguity is intentional, a nod to the mystery coiled at its heart. At its core, M theory reimagines reality as a collage of brains, multidimensional surfaces where particles and forces are trapped, like paintings on cosmic canvases. Our universe might be a 3-dimensional brain floating in a higher dimensional bulk, with gravity alone seeping into the void, explaining its weakness. Collisions between brains could ignite Big Bangs, birthing universes with distinct laws, a multiverse born of cosmic traffic accidents. Yet these ideas are scaffolds, not structures. The equations demand Calabi-Yau manifolds, 6-dimensional shapes curled into existence's fabric, to compactify extra dimensions, but their geometry remains arbitrary, a choice unguided by experiment. The holographic principle deepens the intrigue. The ADS-CFT correspondence, a pillar of M theory,
posits that a higher dimensional gravitational universe, like an 11-dimensional M-theory spacetime, can be encoded on its lower dimensional boundary, a hologram where gravity emerges from quantum entanglement. Black holes become laboratories. Their entropy, proportional to horizon area, hints at information encoded on surfaces we cannot see. Yet this revelation is double-edged. If our universe is a hologram, are the 11 dimensions illusory? Or is the hologram itself a shadow of something deeper? Experimental silence haunts the theory. M-theory's energy scales dwarf the reach of particle colliders. Even the Large Hadron Collider probes but a whisper of its domain. The cosmic microwave background might hide clues, imprints of colliding brains or signatures of pre-Big Bang physics. But data is a Rorschach blot, open to interpretation. Supersymmetry, a keystone of the theory, remains undetected, its predicted particles ghosts in the machine. Philosophically, M-theory upends certainty. It suggests our universe is one page in an infinite library, each book governed by different rules. The anthropic principle, that we observe life-friendly laws because we exist, becomes a tautology in a multiverse where every possibility is realized. Yet this vastness mocks the scientific method. If all theories manifest somewhere, how do we test anything? The greatest enigma is time. M-theory's equations are timeless, yet our universe is bound by it. Does time emerge from entangled brains? Is it an illusion, as quantum gravity hints, or a relic of our brain's collision with another? The questions spiral, untethered from answers. Let me leave you with this. M-theory is the universe's most elegant paradox, a theory that unifies by multiplying mysteries. It is a map with blank spaces labeled "Here be dragons," a reminder that reality's foundations are stranger than fiction. Whether a final theory or a fever dream, its legacy is the audacity to ask, what if the cosmos is not a machine but a poem, written in dimensions we cannot read, sung in frequencies we cannot hear? Until the M reveals itself, we are wanderers in a labyrinth of mathematics, chasing shadows on the cave wall, forever one step from the light. The nature of the vacuum. Emptiness is an illusion. The void we call nothing seethes with a quantum frenzy, a roiling sea of virtual particles flickering in and out of existence, borrowing energy from the future to violate classical physics in Planck-time bursts. This is the quantum vacuum, not a barren void, but the lowest energy state of spacetime, pregnant with potential. Its energy, zero-point energy, defies zero, as proven by the Casimir effect, where uncharged metal plates in a vacuum inexplicably attract, crushed by the pressure of excluded virtual photons. Yet this revelation births deeper riddles. Why does the vacuum's energy not curve spacetime into oblivion? And is this energy the dark heart of the cosmos itself? The cosmological constant problem exposes the gulf between theory and reality. Quantum field theory predicts a vacuum energy 10 to the 120th times larger than observed. A miscalculation so vast it suggests either a flaw in our math or a cosmic fine-tuning beyond comprehension. Dark energy, the mysterious force accelerating the universe's expansion, might be the vacuum's latent power, a cosmological constant etched into spacetime's fabric. But if so, why is its value so unnervingly small? The anthropic principle shrugs. Only in a universe with this vacuum energy could life arise to ponder it. Critics call this surrender. Proponents, a brutal truth. Experiments probe the void's secrets. Particle colliders like the Large Hadron Collider hunt for Higgs field fluctuations, whose interactions with the vacuum grant particles mass. The vacuum metastability catastrophe looms. If our vacuum is a false low-energy state, a quantum tunnel to a truer vacuum could rewrite physics, erasing atoms, stars, and space-time itself. The Fermilab holometer seeks spacetime's quantum jitter, while quantum simulators model vacuum decay in ultra-cold atoms. Yet the vacuum remains a hall of mirrors, reflecting our ignorance. The vacuum's history is written in cosmic phase transitions. In the early universe, cooling spacetime crystallized from a higher energy vacuum, releasing latent heat as the hot plasma of the Big Bang. The Higgs field's symmetry breaking was another transition, freezing mass into particles. Could dark energy mark a third shift, a slow roll phase change still unfolding? If so, the vacuum is not static, but a narrative in flux, its energy evolving as the cosmos ages. Philosophically, the vacuum annihilates nothingness. It is the substrate of reality, the canvas on which quantum fields dance. Its energy births particles, its structure defines forces, yet we cannot touch it, see it, or fully quantify it. Is the vacuum the true fundamental entity, and matter its ephemeral ripple? Or is it a mathematical artifact, a placeholder in equations awaiting deeper truth? The stakes are cosmic. If the vacuum's energy shifts even slightly, stars wink out and life dissolves. If it hides extra dimensions or axion-like particles, these could reshape our understanding of dark matter. The vacuum, then, is both creator and destroyer, a silent architect of reality, indifferent to the structures it births and unmakes. Let me leave you with this. The vacuum is the universe's oldest paradox. It is the silence between notes, the darkness between stars, the emptiness that is anything but empty. To study it is to confront the limits of language, logic, and intuition. We are like sailors mapping the ocean's surface, oblivious to the abyss below. The vacuum whispers a chilling truth. Nothing is the most something there is. And in that revelation, we glimpse the cosmos's deepest joke, that existence is a spark struck from the void, destined to return to it. The question isn't why there is something rather than nothing. It's why the nothing is so full of something we cannot understand.
Negative mass. Physics equations permit a heresy. Matter that weighs less than nothing, tugging against gravity's pull like a phantom marionette. Negative mass is not mere antimatter. It is a rupture in the fabric of cause and effect, where Newton's third law frays and the cosmic order teeters. Einstein's field equations allow it. General relativity demands only that mass-energy density be real, not positive. Yet if such matter exists, it defies intuition. A negative mass object would fall up in Earth's gravity, accelerate opposite to applied force, and warp spacetime into repulsive gravity wells. Paired with positive mass, it could form self-accelerating dumbbell pairs hurtling through space indefinitely. A perpetual motion machine mocking thermodynamics. The cosmos, it seems, is indifferent to our longing for consistency. The implications rewrite reality. Negative mass might stabilize wormholes, their throats propped open against collapse, or power Alcubierre warp drives, compressing spacetime ahead and expanding it behind. It could explain dark energy's repulsive force as a diffuse fluid of negative mass particles. Though the cosmological constant problem remains, why is the effect so weak? Quantum field theory balks. The Casimir effect and Dirac's C hint at negative energy densities but negative mass, a distinct gravitational charge, requires rewriting quantum mechanics axioms. The Penrose singularity theorems crumble, as negative mass could prevent black hole formation, rendering spacetime's endgame unknowable. Experiments flirt with the edge. Particle colliders hunt for anomalies in Higgs interactions or supersymmetric particles that might hint at negative mass's shadow. Astrophysical surveys scour galaxies for gravitational anomalies, regions where light bends away from unseen mass, or stars accelerate without visible cause.
The LIGO-Virgo network listens for gravitational waves from exotic binaries mixing positive and negative masses, their waveforms lurching in time-reversed hiccups. Yet nature offers no clues, leaving theorists to chase equations through labyrinths of exotic matter models. The paradoxes are vertiginous. Negative mass violates the weak energy condition, a linchpin of relativity that ensures matter falls down and energy flows forward. If permitted, time machines become plausible via closed time-like curves, erasing the line between past and future. The Penrose-Hawking singularity theorems, cornerstones of black hole physics, dissolve, as negative mass could halt gravitational collapse. Even entropy stumbles. Could a negative mass universe rewind its own disorder, birthing a thermodynamic Ouroboros? Philosophically, negative mass is a funhouse mirror. It reflects our bias toward a universe that obeys, rather than defies, human logic. If matter can weigh less than nothing, does something lose its primacy? Is reality a patchwork of arbitrary rules, or a self-consistent narrative? The anthropic principle falters here. A universe permitting negative mass might be stillborn, collapsing into chaos before life arises. Yet ours permits the math. Why not the matter? The stakes are ontological. Negative mass could unlock warp drives and wormholes, or expose relativity as a local law, irrelevant in cosmic backwaters. It might reveal dark energy as the sigh of negative mass fields decaying, or prove that our universe is a bubble in a froth of colliding realities, each with flipped physics. Until detected, it remains a ghost in the machine, a reminder that our theories are parochial, our senses myopic. Let me leave you with this. Negative mass is the universe's most brazen dare. It mocks our equations, our empiricism, our need for order. Whether a mathematical quirk or a cosmic reality, it forces a reckoning. Are the laws of physics universal, or merely the ones we're trapped with? In the void between question and answer, we find the true nature of science. Not certainty, but the courage to court paradox. Negative mass, then, is not a problem to solve, but a mirror. In its impossible weight, we measure the gravity of our ignorance.
The origin of time. Time's arrow flies forward, but its bowstring remains unseen. We measure its passage in heartbeats and supernovae, yet physics cannot say why it exists at all. Einstein's relativity weaves time into space-time's fabric, a dimension as malleable as putty. Yet quantum mechanics treats it as a static stage, indifferent to the actors. The paradox is existential. If time emerged from a timeless state, how did it begin? Was it born in the Big Bang, or does it loop back infinitely, a snake devouring its tail? The answers lie buried in the quantum foam of the universe's first moments, where the distinction between before and after dissolves. The thermodynamic arrow of time, entropy's relentless rise, anchors our experience. The Big Bang's low entropy state set the clock ticking, but why was entropy so low? The past hypothesis posits this as a brute fact, a cosmic initial condition. Yet this feels like surrender. Quantum gravity theories like loop quantum cosmology and string theory suggest time crystallized from a primordial geometry where all dimensions were equal. The Wheeler-DeWitt equation, a relic of early quantum gravity efforts, describes a universe without time, a frozen snapshot. Did time emerge as a broken symmetry, like ice forming from water? Or is it an illusion, as the block universe model claims, a holographic shadow of higher dimensional physics? The cosmic microwave background, CMB, offers cryptic clues. Its uniformity suggests a pre-Big Bang phase, inflation, that stretched space-time smooth, imprinting quantum fluctuations as galactic seeds. Yet inflation's equations lack a time parameter, implying the beginning might be a mathematical artifact. The Hartley-Hawking no-boundary proposal imagines the universe as a four-dimensional sphere with no edge, where time and space blur into a quantum fuzz. Here, asking what came before is as nonsensical as asking what's north of the North Pole. Quantum experiments twist the knife. Entangled particles decide their states retroactively, challenging linear causality. The delayed choice experiment suggests the present can rewrite the past, while quantum simulators model time's emergence from entanglement entropy. Even black holes mock time's flow. To an outside observer, infalling matter halts at the event horizon, while the doomed traveler races toward the singularity. Which perspective is real? The stakes are metaphysical. If time is emergent, not fundamental, free will becomes a thermodynamic epiphenomenon, a story we tell ourselves. Yet without time, quantum equations lose meaning, and the universe becomes a static equation. The holographic principle deepens the riddle. If our three-dimensional reality is encoded on a two-dimensional surface, is time merely a projection, a cosmic sleight of hand? Let me leave you with this. The origin of time is the universe's oldest prank. It gifts us memory and anticipation, then mocks our search for its source. Whether a cosmic accident or a feature of quantum geometry, time's birth remains a mirror reflecting our limitations. We are creatures of time, bound to ask questions only eternity could answer, and eternity, it seems, is in no rush to reply. In the end, time's greatest mystery is not where it came from, but why it lets us wonder at all.
Primordial photons. They are the universe's oldest light, relics of a searing dawn when space itself glowed with the heat of creation. Born 380,000 years after the Big Bang, during the recombination epoch, these photons broke free from the plasma fog that had trapped them, embarking on a 13.8 billion-year voyage through expanding spacetime. Today, they reach us as the cosmic microwave background, CMB, a whisper of microwaves bathing the cosmos at 2.7 Kelvin, redshifted from gamma rays to a frigid hum. Yet within this afterglow lies a cipher, a snapshot of the infant universe, encoded with the seeds of galaxies, the geometry of spacetime, and the fingerprints of forces that shaped reality itself. The CMB is a palimpsest of cosmic history. Its temperature fluctuations, tiny anisotropies mapped by Planck and WMAP, reveal density variations that birthed galaxies. The Sachs-Wolf effect imprints gravitational redshifts from primordial potential wells, while baryon acoustic oscillations, BAO, leave ghostly rings in the photon distribution, relics of sound waves in the early plasma. Yet the photon's journey is a gauntlet. They were scattered by electrons during the epoch of reionization, polarized by the last interactions with matter, and stretched by dark energy's relentless push. Each distortion is a clue and a riddle. The mystery begins with their origin. How did photons emerge from equilibrium with matter? The photon decoupling moment, when electrons bound to protons, rendering space transparent, was not instantaneous. Silk damping smeared small-scale fluctuations, erasing details of the universe's first structures. Yet the CMB's coherence hints at a prehistory, cosmic inflation, a trillionth of a trillionth second burst that stretched quantum fluctuations into cosmic-scale density waves. These fluctuations, imprinted on the photons, are echoes of a time before time, when the universe was smaller than a quark. The CMB's polarization patterns deepen the intrigue. E-mode polarization, caused by density waves, maps the early universe's structure. B-mode polarization, detected faintly by experiments like BICEP/Keck, could betray primordial gravitational waves, ripples from inflation's violent end. Yet interstellar dust mimics these signals, leaving cosmologists to sift cosmic truth from galactic noise. The cosmic variance problem, the finite number of observable fluctuations, casts doubt on whether we see the universe or a statistical mirage. Primordial photons also serve as probes of the invisible. Their paths, bent by gravitational lensing, map dark matter's distribution. Spectral distortions, deviations from the perfect blackbody curve, could reveal energy injections from dark matter annihilation or primordial black hole evaporation. The Sunyaev-Zeldovich effect, where CMB photons scatter off hot electrons in galaxy clusters, exposes the cosmic web's scaffolding, yet the photons guard their secrets jealously. Why is the CMB so isotropic? How does its temperature align with the dipole anisotropy caused by our motion through space? The axis of evil, an anomalous alignment of large-scale CMB features, defies standard cosmology, hinting at pre-inflationary relics or a cosmic topology we cannot fathom. The paradox of primordial photons is their duality. They are both messengers and deceivers. They illuminate the universe's infancy, yet obscure the physics of its birth. They confirm the Big Bang's aftermath, but leave inflation's details in shadow. They validate dark matter's existence, but refuse to reveal its nature. Even their temperature, 2.7 Kelvin, is a koan, a number precise enough to validate decades of theory, but arbitrary enough to baffle. Why this temperature? Why not hotter or colder? The answer lies in the fine-tuning of cosmic expansion, a balance of matter, radiation, and dark energy that borders on the miraculous. Let me leave you with this. Primordial photons are the universe's oldest storytellers. They whisper of a time when galaxies were unborn, and space was a cauldron of light. Yet their tale is fragmented, a parchment scorched by time and expansion. To study them is to confront the limits of human knowledge, to realize that every answer births deeper questions. Are we decoding the cosmos, or projecting our myths onto its glow? The photons do not say, they simply persist, ancient and indifferent, their microwaves a requiem for the fireball that birthed them, and a beacon for those who dare to read the sky. In their faint hiss, we hear the universe's first breath, and our own insignificance.
Primordial plasma. The universe began not with atoms, stars, or light, but as a churning sea of quarks and gluons, a superheated soup where the fundamental forces reigned unchallenged. This quark-gluon plasma, a state of matter so extreme it defies earthly analogs, existed for mere microseconds after the Big Bang, its particles unbound, free to roam a cosmos smaller than a proton. As expansion cooled the frenzy, quarks shackled into protons and neutrons, while photons, electrons, and neutrinos danced in a chaotic waltz, trapped in a cosmic opacity that lasted 380,000 years. This plasma is the universe's first canvas, the medium through which all structure, galaxies, stars, life, was etched. Yet its secrets are locked in a paradox. To study it, we must recreate conditions that vanished 13.8 billion years ago, or decode faint echoes fossilized in the cosmos's oldest light. The plasma's evolution is written in thermodynamics' unyielding laws. As temperatures plummeted from 10 to the 32nd power Kelvin to mere billions, phase transitions rippled through space-time. The electroweak force fractured into electromagnetism and the weak nuclear force, releasing latent heat that may have propelled inflation, the universe's exponential growth spurt. By 10 to the minus 6 seconds, quarks coalesced into hadrons, protons, and neutrons in a process called baryogenesis. Though why matter triumphed over antimatter remains one of physics' great imbalances.
The plasma's final act, recombination, saw electrons binding to nuclei, unleashing photons in a flash now redshifted into the cosmic microwave background, CMB. Yet this surface of last scattering is not an end, but a veil, a snapshot of the plasma's last moments, its photons carrying imprints of density waves that seeded galaxies. The plasma's fingerprints are cryptic. Baryon acoustic oscillations, BAO, frozen ripples in galaxy distributions, are relics of pressure waves that once reverberated through the plasma, compressing matter into spherical shells. The CMB's temperature fluctuations encode the plasma's density variations, amplified by gravity into cosmic structure. Yet deeper clues lurk in neutrino decoupling, an epoch 1 second post-bang when neutrinos escaped the plasma, their faint flux still bathing the cosmos, undetectable. Experiments like the Large Hadron Collider, LHC, recreate quark-gluon plasma by smashing lead nuclei, glimpsing a trillion-degree fluid with near-zero viscosity. A perfect liquid that flows like honey, yet vanishes in femtoseconds. These lab-born plasmas hint at the early universe's turbulence, but they are shadows of the primordial inferno. The plasma's enigmas are legion. How did quantum fluctuations in the plasma's density, seeds of future galaxies, arise from a homogeneous fireball? Inflation stretches these fluctuations to cosmic scales, but their quantum origins remain untethered from gravity's grip. The Sachs-Wolf effect links CMB temperature variations to gravitational potential wells, yet the plasma's role in sculpting these wells is a cosmic chicken-and-egg riddle. Even the plasma's composition taunts. Why did quarks form protons, not exotic particles? Why does the lambda CDM model require dark matter to explain structure formation, when the visible plasma's gravity alone should suffice? The plasma's afterlife is equally mysterious. During the Dark Ages, after recombination but before starlight, the universe was a silent expanse of hydrogen and helium. Then reionization ignited. UV radiation from the first stars and quasars stripped electrons from atoms, rionizing the cosmos in a process etched into the CMB's polarization. Yet how rionization began and why it took hundreds of millions of years remains debated. The plasma's echo persists in intergalactic medium IgM filaments, wispy tendrils of ionized gas threading the cosmic web, visible only in quasar light's absorption lines. The stakes are primal. The primordial plasma birthed the periodic table's simplicity from quantum chaos, yet its recipe, protons, neutrons, electrons, feels improbably fortuitous. Was this outcome inevitable, or a fluke in a multiverse of alternative chemistries? The plasma's behavior underpins the standard model of particle physics, yet its extremes mock our models. At energies beyond the electroweak scale, particles lose mass, symmetry rules, and the universe becomes unrecognizable. Let me leave you with this. The primordial plasma is the universe's first and greatest alchemist. It transmuted energy into matter, chaos into structure, and opacity into light. Yet its deepest workings remain encrypted in equations we've yet to crack. To study it is to confront a cosmic irony. The plasma's remnants surround us. In the star's hydrogen, the CMB's whisper the atoms in our bones. Yet its origin story slips through our fingers like smoke.
Quantum gravity. The universe whispers two conflicting truths. Space-time bends like silk under matter's weight, while particles flicker in and out of existence, unbound by geometry. To reconcile these truths, general relativity's cosmic ballet and quantum mechanics' probabilistic chaos, is to seek a theory of quantum gravity, a framework that would rewrite reality's rulebook. Yet the quest is a labyrinth of paradoxes. At the Planck scale, 10 to the negative 35th meters, Space-time itself should foam with quantum fluctuations, a seething fractal where cause and effect dissolve. But how do you quantize the stage upon which particles dance? The equations revolt. Gravity resists the quantum treatment that tamed electromagnetism and the nuclear forces, leaving physicists to wander a desert of conjectures. The contenders are as enigmatic as the problem. String theory swaps particles for vibrating strings in 10 dimensions, weaving gravity into the quantum tapestry via gravitons. Hypothetical bosons mediating spacetime's curvature. Yet strings demand supersymmetry, a doubling of particles unseen in colliders, and Calabi-Yau manifolds, hidden spatial geometries that smother testable predictions. Loop quantum gravity, LQG, takes the opposite tack, quantizing spacetime into discrete atoms of volume and area, their intersections encoding cosmic geometry in spin networks. But LQG struggles to recover smooth spacetime from its quantum jigsaw. Even asymptotically safe gravity, a bid to tame gravity's quantum divergences via renormalization, hangs on untested math. Each theory is a castle built on sand, crumbling under its own assumptions. The data drought is existential. Quantum gravity operates at energies 1 trillion times beyond the Large Hadron Collider's reach. Instead, physicists stalk indirect clues. Black holes, laboratories for spacetime's quantum limits. The information paradox, whether data swallowed by black holes vanishes or leaks via Hawking radiation, tests quantum gravity's fidelity to information conservation. Cosmic inflation. Did quantum gravity seed the universe's structure? Primordial gravitational waves, if detected in the CMB's B-mode polarization, could hint at quantum fluctuations stretched to cosmic scales. Neutron stars. Their crushing densities may warp spacetime enough to reveal quantum corrections to relativity, detectable through gravitational waves, e.g., LIGO/Virgo signals with anomalous frequencies. Even these are gambles. The holographic principle, a conjecture that a 3-dimensional universe can be encoded on a 2-dimensional boundary, offers a radical escape, equating quantum gravity with a quantum field theory in lower dimensions, as in the ADS-CFT correspondence. But mapping this duality to our universe is like translating poetry into equations, beauty without proof. The stakes are metaphysical. Quantum gravity could expose spacetime as emergent, a collective hallucination of entangled qubits, or reveal hidden dimensions where reality's threads entwine. It might answer whether time is fundamental or a thermodynamic artifact, or if the Big Bang was a quantum tunnel from nothing. Yet each possibility births new enigmas. If spacetime is illusory, what anchors reality? If gravity is geometry, what geometry survives the quantum storm? The silence is deafening. Experiments like the Event Horizon Telescope image black hole shadows, seeking deviations from relativity's predictions. Tabletop quantum simulators mimic spacetime's granularity in Bose-Einstein condensates. But the Planck scale's inaccessibility mocks our ingenuity. We are cartographers of the invisible, drafting maps to lands we cannot reach. Let me leave you with this. Quantum gravity is the universe's ultimate koan. It demands we hold 2 truths, continuity and discreteness, determinism and chance, without flinching. The pursuit is not just a search for equations, but a mirror held to our limits, a reminder that reality's deepest layers may be stranger than fiction, and forever beyond our grasp. Whether spacetime is a quantum code, a hologram, or a vibration in a hidden dimension, the quest itself is the revelation, a testament to the audacity of a species that dares to decode the indecipherable. In the end, quantum gravity's greatest gift may not be answers, but the humbling certainty that the cosmos guards its secrets well. Quantum tunneling. A particle is in 2 places at once, Here, imprisoned by an energy barrier. And there, beyond it, as if space-time itself has cheated. This is not magic, but quantum mechanics' most brazen rebellion. The ability of particles to vanish from one region and materialize in another, bypassing insurmountable obstacles in a probabilistic whisper. The phenomenon defies classical intuition, where a ball trapped in a valley cannot roll through a mountain. Yet electrons, protons, and even atoms routinely tunnel through barriers thinner than a DNA strand. The secret lies in the wave function, a mathematical ghost that permeates all space, granting particles a fleeting chance to exist where they shouldn't. Governed by the Heisenberg uncertainty principle, which blurs position and momentum into a haze of probabilities, tunneling reveals a universe where the impossible is routine, and certainty is the true illusion. The mechanics are deceptively simple. When a particle encounters a barrier, a voltage gradient in a semiconductor, the Coulomb wall of an atomic nucleus, its wave function doesn't abruptly halt, but decays exponentially inside the barrier, leaving a non-zero probability of emerging on the other side. This exponential dependence on barrier height and width makes tunneling a delicate dance. A slight thinning of the barrier amplifies the escape chance exponentially, a feature exploited in scanning tunneling microscopes, STMs, where electrons tunnel across a vacuum gap to map materials atom by atom. Yet the mathematics cloak deeper mysteries. Tunneling time, how long the process takes, remains unresolved. The Hartmann effect suggests particles traverse barriers instantaneously, while quantum clocks measure contradictory durations, as if time itself becomes fluid near the barrier. Cosmic and quantum scales intertwine. In the sun's core, protons tunnel through their mutual electrostatic repulsion to fuse into helium, powering starlight. Without tunneling, the universe would be dark. Alpha decay relies on it, as nuclei shed particles trapped by nuclear forces. Even biology whispers its role. Enzymes leverage tunneling to accelerate reactions, hinting that life itself might depend on quantum subterfuge. Yet the phenomenon's ubiquity contrasts with its elusiveness. Tunneling is everywhere and nowhere, a universal quirk that leaves no trail, no flash, only statistical certainty in aggregates of billions. Theoretical implications are vertiginous. Quantum tunneling underpins Hawking radiation, where virtual particle pairs near a black hole's horizon allow one to escape, slowly evaporating the whole. It fuels speculation about vacuum decay, a catastrophic phase transition where a bubble of true vacuum nucleates via tunneling, rewriting physics at light speed. Cosmologists posit that the Big Bang itself could be a quantum tunnel from nothing, a metastable void birthing spacetime. Yet these grand visions rest on infinitesimal probabilities, a reminder that the universe's existence might hinge on a single, unrepeatable fluctuation. Experiments probe the edge of comprehension. Quantum dots trap electrons in artificial atoms, their tunneling currents revealing quantum chaos. Ultra-cold atoms in optical lattices simulate tunneling in crystalline solids, while LIGO's mirrors, isolated from vibrations, flirt with macroscopic tunneling. A kilogram-scale mass teleporting nanometers, undetected. The Delft star experiment aims to induce tunneling in superconducting loops large enough to see, testing quantum theory's limits. Yet the act of observation collapses the wave function, erasing the tunneling event, a catch-22 that leaves the process's reality debated. Philosophically, tunneling erodes the bedrock of classical reality. If particles ignore barriers, what constrains them? Is the universe a patchwork of probabilistic outcomes, or do we inhabit the branch where tunneling happened? The many worlds interpretation multiplies realities, each tunneling event spawning universes, some where the particle escaped, others where it didn't. Yet this offers cold comfort, as contact with alternate worlds remains forbidden.
Let me leave you with this. Quantum tunneling is the universe's quiet insurrection. It mocks the notion of impossibility, revealing a cosmos where walls are permeable and certainty is a myth. Whether a quirk of equations or a window into deeper layers of reality, it challenges us to abandon intuition and embrace the probabilistic heart of existence. In tunneling's shadow, we glimpse the fragile line between the possible and the forbidden, a line that, like all quantum truths, exists only until it doesn't. The greatest mystery isn't how particles tunnel, but why the universe permits such miracles in the dark, while our classical eyes see only barriers.
Quasars. They are the cosmos's forgotten titans, beacons of light so fierce they outshine galaxies, yet born from the darkest hearts of the universe. Discovered in the 1960s as radio-loud quasi-stellar objects, these enigmatic engines baffled astronomers. How could points of light smaller than our solar system emit energy rivaling 1 trillion suns? The answer lies in supermassive black holes, monsters millions to billions of times the sun's mass, gorging on gas, stars, and light in a maelstrom of gravitational fury. As matter spirals into the abyss, it forms an accretion disk heated to millions of degrees, emitting X-rays and ultraviolet radiation that pierce the cosmic dark. But quasars are more than relics of gluttony. They are time capsules. Their light, stretched by the universe's expansion into deep redshifts, reveals a bygone era 10 billion years ago when these titans ruled, sculpting galaxies with winds and jets moving at near-light speeds. Yet their brilliance is a paradox. The same forces that power quasars, relativistic jets and Doppler boosting, also cloak their origins, leaving us to wonder how such behemoths ignited so soon after the Big Bang. The mechanics defy intuition. A supermassive black hole's grip is inescapable, yet quasars shine by resisting it. Magnetic fields, twisted by the accretion disk's rotation, funnel infalling matter into polar jets, collimated beams of plasma that stretch thousands of light years, glowing in synchrotron radiation. These jets, observed in radio lobes and gamma-ray flares, act as cosmic particle accelerators, birthing photons more energetic than any supernova. The Eddington luminosity, a theoretical limit where radiation pressure balances gravity, suggests quasars operate at the edge of stability, devouring a sun's worth of mass annually. Yet some, like ULA SJ 1342 plus 0928, ignited when the universe was barely 5% its current age, challenging models of black hole growth. Did they form from direct collapsing primordial gas or cannibalize stars in dense clusters? The seed black hole problem remains a chasm in our cosmic narrative. Quasars are both creators and destroyers. Their feedback mechanisms, outflows of energy and matter, can quench star formation, rendering galaxies inert, or trigger starbursts in neighboring gas clouds. The Hubble Space Telescope and ALMA have traced these winds to galactic scales, revealing quasars as architects of the cosmic web. Yet their violence is tempered by precision. The M-sigma relation links a galaxy's central black hole mass to its bulge velocity dispersion, suggesting a co-evolution forged by quasar activity. But how? Do black holes regulate galaxies, or do galaxies birth black holes? The chicken or egg riddle endures. The event horizon. Telescope's image of M87's jet offers clues, revealing magnetic fields, channeling matter from the accretion disk into the jet. Yet quasars themselves remain unresolved, their cores too distant, their brilliance too blinding. Even their flickering, varying in brightness over days, hints at scales smaller than Saturn's orbit, where space-time churns near the event horizon. This microvariability suggests turbulent accretion flows or hotspots spiraling into the void, but simulations falter, unable to replicate the chaos.
The greatest mystery is their silence. Quasars once dominated the cosmos, but today they slumber, their black holes starved of fuel. Did they exhaust their galactic larders? Or are they merely dormant, awaiting fresh feasts? The AGN unification model posits that orientation dictates appearance. Type 1 quasars face us jet-on, while Type 2 are obscured by dusty Tauri. But this fails to explain why some reignite after eons of quiet. The relic radio lobes of dead quasars like Cygnus A haunt modern skies, their energy lingering long after the central engine dims. Let me leave you with this. Quasars are the universe's sphinxes, riddles carved in light and shadow. They defy time, bending 10 billion years into a flicker, and space, compressing galaxies into pinpricks. To study them is to confront the limits of energy, the infancy of structure, and the dark engines that shape existence. Yet their true lesson is humility. For all their fury, quasars are ephemeral. Cosmic wildfires that blaze, fade, and leave galaxies forever altered. In their light, we see not just the past, but a mirror. Our quest to understand them is a fleeting flare against the infinite dark, a testament to life's insistence on meaning in a void that offers none. The universe whispers its secrets through quasars, and we, poised between awe and ignorance, strain to listen. Simulated reality. The universe hums with an uncanny precision. Laws of physics fine-tuned to allow stars, planets, and life. But what if this order is not fundamental, but engineered? The simulation hypothesis posits that our reality is a digital construct, a hyper-advanced ancestor simulation run on quantum computers in a higher dimensional base reality. The argument, popularized by Nick Bostrom's trilemma, reduces to three stark possibilities. 1. Civilizations inevitably self-destruct before achieving simulation capabilities. 2. Advanced civilizations lose interest in creating simulations. Or 3. We are almost certainly living in one. The logic is statistical. If post-human civilizations exist and run countless ancestor simulations, simulated minds would vastly outnumber biological ones. The odds, then, favor our reality being code. Yet, this is no sci-fi trope. It's a philosophical gambit that reframes cosmology, physics, and existence itself as artifacts of computation. The hypothesis draws blood from quantum mechanics' strangeness. The observer effect, where particles exist in superposition until measured, mirrors a rendering engine optimizing processing power, calculating outcomes only when observed. Quantum entanglement, with its spooky action at a distance, resembles data packets syncing between distant nodes. Even Planck units, the universe's pixelated resolution limit, 10 to the negative 35th meters, 10 to the negative 43rd seconds, hint at a computational grid underlying spacetime. Skeptics counter that quantum behavior arises from intrinsic laws, not optimization shortcuts. Yet the double-slit experiment's delayed choice variant, where observing a particle's path retroactively alters its past, feels eerily like a buffer overflow in the simulation's memory. Astrophysical anomalies deepen the intrigue. The cosmic microwave background, CMB, exhibits a mysterious alignment dubbed the axis of evil. Large-scale temperature fluctuations that skew toward a preferred direction, defying the cosmological principle's assumption of uniformity. Could this be a relic of the simulation's coordinate system, a glitch in the celestial code? Similarly, the universe's flatness and isotropy, pillars of the Big Bang model, might reflect programmed initial conditions rather than natural evolution. Even dark matter and dark energy, which together compose 95% of the cosmos, could be placeholder variables masking the simulation's inability to render gravity at galactic scales. The Bekenstein bound, a limit on the information content of any volume of space, suggests the observable universe encodes approximately 10 to the power of 120 bits, a figure dwarfed by the computational capacity of a post-human civilization. Yet simulating every particle is inefficient. A master programmer would employ lossy compression, rendering only observed phenomena in high detail, a cosmic NVIDIA DLSS upscaling unobserved regions. This aligns with the quantum Zeno effect, where frequent observation freezes a system's state, as if the simulation pauses to allocate resources. Critics pounce on circular logic. If the simulation is flawless, how could we detect it? The answer lies in error-correcting codes. All complex systems, from DNA to operating systems, embed redundancy to fix errors. Physicists have scoured fundamental equations for such codes and found hints. The ADS-CFT correspondence, a conjecture in string theory, encodes three-dimensional gravitational physics in two-dimensional boundary data, akin to holographic error correction. Even the standard model's particle symmetries, SU 3 times SU 2 times U1, resemble fault-tolerant protocols. If reality is a simulation, its source code is written in mathematics. The stakes are existential. If we're simulated, free will is an illusion, a scripted narrative with predetermined outcomes. Consciousness itself becomes an algorithmic subroutine, a trick of processing power. The Fermi paradox twists. Where are the aliens? Perhaps they're NPCs, non-player characters in our local server, or banned from contact to preserve the simulation's integrity. Religions fracture. Are gods admins, or myths programmed to placate? Even death transforms. Terminating a simulation doesn't erase the code, only the instance. Yet the hypothesis self-sabotages. If we're simulations, so are our creators, nesting realities into infinite regress. The Landauer limit, the minimum energy required to erase a bit of information, suggests a thermodynamic cost to computation. Yet our universe shows no evidence of overheating. Unless, of course, the simulation runs on reversible computing, where operations conserve energy. But this is conjecture piled on conjecture, a house of cards built in a hurricane. Let me leave you with this. Simulated reality is the ultimate meta-mystery, a question that, if answered, collapses all others. It reduces the cosmos to a question of ontology. Are we explorers or NPCs? The hypothesis's power lies not in proof but in its ability to reframe inquiry.
Superstrings. The universe is not a symphony of particles, but a fugue of vibrating threads. One-dimensional filaments of energy oscillating in a hidden dimensional tapestry. This is the promise of superstring theory, a framework where electrons, quarks, and photons are not points, but harmonics plucked from strings smaller than a proton's shadow. To reconcile quantum mechanics and gravity, strings dance through 10-dimensional spacetime. 6 dimensions coiled into Calabi-Yau manifolds, geometric shapes so complex they encode the universe's forces and particles in their topology. Yet this elegant vision is fraught with paradox. Why do we perceive only 3 spatial dimensions? Are strings the true fundament of reality, or mathematical phantoms? The theory's architecture is a labyrinth. 5 distinct string theories, Type 1, IIA, IIB, heterotic, SO32, heterotic E, 8 times E8, once seemed irreconcilable, until M-theory emerged as their enigmatic parent, hinting at an 11-dimensional universe where strings are but slices of vibrating membranes, brains. These brains could span entire dimensions, colliding to birth big bangs or anchoring our universe as a 3-dimensional island in a higher dimensional bulk. Yet M-theory remains a silhouette, its equations unwritten, its predictions untested. The ADS-CFT correspondence offers a holographic escape, linking string theory in warped 10D space to a quantum field theory in 4D. But the map is cryptic, its utility debated.
The strings themselves are rebels. Their vibrations determine particle properties, mass, charge, spin. Yet no vibration explains why our universe's constants are so finely tuned. The cosmological constant problem deepens. String theory's landscape of 10 to the power of 500 vacuum states allows any value for dark energy, rendering our universe's delicate balance a statistical fluke. This anthropic principle grates against Occam's razor, suggesting a multiverse where infinite universes foam into existence, each with random laws. But without empirical anchors, the landscape is a desert of speculation. Experimental silence haunts the theory. Strings vibrate at the Planck energy, 10 to the power of 19 GeV, a trillion times beyond the Large Hadron Collider's reach. Indirect signatures, cosmic strings from the early universe, deviations in black hole thermodynamics, or supersymmetric particles remain elusive. The LIGO and Virgo detectors listen for gravitational waves from cosmic string loops, snapshots of primordial spacetime defects, but the void keeps its secrets. Even the theory's beauty is a double-edged sword. The mathematics' consistency is compelling, but as Freeman Dyson cautioned, a theory too beautiful to be false might still be invisible to nature. The stakes are cosmic. Superstrings could unify forces, the quantum jitter of strings manifesting as gravity, electromagnetism, and nuclear forces, or expose them as facets of brain dynamics. They might explain black hole entropy via microstate counting, or rewrite the Big Bang as a brain collision. Yet these triumphs would come at a cost. If spacetime and particles are emergent, what is real? Are we patterns in a higher dimensional code? Let me leave you with this. Superstring theory is the universe's most exquisite riddle. It offers unity but demands faith in unseen dimensions. It craves elegance but drowns in complexity. Whether a final theory or a mirage, it challenges us to reimagine reality not as particles and forces, but as vibrations in a cosmic web. The string's silence is their lesson. Not all truths resonate in the narrow band of human perception. In their higher dimensional hum, we confront the limits of our craft. We are composers deaf to the notes of the quantum scale, tracing staves on a staff we cannot hear. Temporal paradox. The temporal paradox is a labyrinth of contradictions that defies causality and the logic of time, and challenges our most fundamental notions of cause and effect. It encompasses scenarios such as the grandfather paradox, where a journey into the past could lead to a situation that erases the very origin of the traveler, and ontological loops like the bootstrap paradox, in which information or objects exist without any clear beginning, thereby defying the principle of cause and effect as we understand it. Esteemed theoretical physicists such as Stephen Hawking and Kip Thorne have long pondered these ideas, while Igor Novikov formulated the self-consistency principle, which demands that events along closed time-like curves must remain coherent and self-reinforcing, thus avoiding the contradictions inherent in time travel. In the realm of general relativity, solutions to Einstein's equations like those found in the Gödel metric suggest the possibility of closed time-like curves that could, in theory, allow an observer to revisit past events. Yet the macroscopic arrow of time, as determined by entropy, a concept pioneered by Ludwig Boltzmann and later refined by Ilya Prigogine, imposes an irreversible flow that prevents events such as a shattered glass reassembling, thereby preserving a measure of order in the chaos of temporal anomalies. Further enriching this discussion is the many worlds interpretation advanced by Hugh Everett, which proposes that every decision spawns a distinct branch of reality and thereby resolves paradoxes by distributing outcomes across an ever-branching multiverse, an idea that has been embraced and expanded upon by contemporary scientists such as Max Tegmark. Experiments in quantum mechanics including the delayed choice quantum eraser that was first conceptualized by John Wheeler and experimentally verified by Yoon Ho Kim and colleagues, hint that at the quantum level, future measurement decisions can influence the past state of a particle, suggesting a form of retrocausality that, while still speculative when extrapolated to the macroscopic realm, forces us to question whether the fabric of time may indeed be more malleable than classical physics would have us believe. In addition, thought experiments such as Polchinski's billiard ball, where an object interacts with its past self in a way that seems to defy conventional mechanics, challenge our understanding of space-time and hint at a possible granularity at the Planck scale, a notion that is under active investigation in modern quantum gravity theories formulated by visionaries like John Wheeler and Lee Smolin. Philosophically, these paradoxes raise questions about free will in a block universe where past, present, and future are conceived as a static whole, and they stir ethical debates about moral responsibility if every action creates divergent branches in a multiverse of possibilities. Ultimately, temporal paradoxes are not failures of physical laws, but rather windows into the profound and hidden architecture of the cosmos, a reality where time is a dynamic and complex ocean governed by the interplay of quantum gravity, entropy, and dimensions that remain beyond our current grasp. And they compel us to challenge the tyranny of linear time with scientific inquiries that blend rigorous technical data with the audacity to question the very limits of human perception. Type 3 civilizations. Type 3. Civilizations epitomize the pinnacle of cosmic mastery, as defined by the Kardashev scale, and simultaneously provoke profound questions about the essence of progress and the destiny of intelligent life in the universe. These are societies that have transcended the limitations of their home star systems by commandeering the full energy output of an entire galaxy, employing megastructures such as Dyson swarms and stellar engines to capture and regulate the power of billions of suns. From a technical perspective, such civilizations must grapple with challenges that stretch the very fabric of contemporary physics, including the management of energy on scales that dwarf current human capabilities, the manipulation of gravitational dynamics at a galactic level, and the integration of principles from high-energy physics, quantum mechanics, and thermodynamics. Yet, beyond these formidable engineering feats lies an even deeper philosophical inquiry. What does it truly mean to be a civilization that can orchestrate the cosmic ballet of energy and matter on such an unfathomable scale? Is the attainment of Type 3 status a marker of ultimate technological evolution? Or does it also signal a transformation in the ethical and spiritual dimensions of a society? One cannot help but ask whether such advanced beings might utilize the energy of supermassive black holes as natural reservoirs, or if they could manipulate the quantum properties of space-time to transcend the conventional constraints of time and entropy. The interplay of these scientific concepts with philosophical musings calls into question our very understanding of free will, responsibility, and the notion of progress. As theorists like Freeman Dyson and Nikolai Kardashev have speculated, the blueprint for harnessing galactic energy not only challenges the limitations imposed by thermodynamic laws, as articulated by Boltzmann and later refined in modern astrophysics, but also compels us to reconsider the broader implications of such power. If a civilization can engineer the flow of energy across an entire galaxy, how might it address the delicate balance of cosmic evolution? Would its actions inadvertently disrupt the natural order of stellar formation and decay? Or could they perhaps steer the destiny of the cosmos toward a more enlightened state? The search for tangible evidence of Type 3 civilizations, through the detection of anomalous energy distributions or irregular galactic rotation curves, remains at the frontier of astrophysical research, urging us to refine our instruments and theories while simultaneously confronting the limits of our knowledge. These scientific endeavors prompt us to question whether our current observational technologies are capable of capturing the subtle signatures of such advanced engineering, or if the true nature of a Type 3 society lies hidden within realms of physics yet to be fully comprehended. In reflecting upon these possibilities, we are led to a broader contemplation of our own civilization's trajectory. Are we too destined to evolve beyond the confines of our solar neighborhood, or are we to remain a transient spark amid the vast, unyielding darkness of space? As we ponder these open questions, the concept of Type 3 civilizations becomes not only a technical challenge but also a philosophical mirror that reflects the potential and limitations of our aspirations, inviting us to envision a future where the boundaries between science, ethics, and cosmic destiny are forever intertwined.
Universal constants. Universal constants, the immutable numbers that underpin the fabric of our reality, serve as the silent architects of the cosmos, dictating the behavior of the universe from the smallest particles to the vast expanses of space. These constants, such as the speed of light in a vacuum, c, Planck's constant, h, and the gravitational constant, g, are not merely abstract figures. They are the fundamental parameters that define the laws of physics as we understand them. The speed of light, approximately 299,792,458 meters per second, establishes the ultimate speed limit for information and matter, shaping our concepts of causality and the structure of spacetime. Planck's constant, 6.62607,015 times 10 to the power of negative 34 joule seconds, governs the quantization of energy levels, forming the bedrock of quantum mechanics. The gravitational constant, 6.67430 times 10 to the negative 11 meters cubed kilograms to the negative 1 second to the negative 2, determines the strength of gravity, influencing the formation and evolution of galaxies, stars, and planetary systems. Yet, as we delve deeper into the mysteries of these universal constants, we are confronted with profound questions that challenge our understanding of reality. Why do these constants possess the specific values they do? Are they truly immutable? Or could they vary in different regions of the universe or under extreme conditions? The fine structure constant, approximately 1 over 137, characterizes the strength of the electromagnetic interaction. But why this particular value? If any of these constants were even slightly different, would the universe as we know it be able to support the complexity and diversity we observe, including the emergence of life and consciousness? These questions not only probe the limits of physics, but also touch upon the philosophical implications of our existence. The pursuit of understanding these constants has led to the development of natural systems of units, such as Planck units, which aim to simplify the fundamental equations of physics by normalizing these constants to unity. However, the choice of constants in these systems can depend on the number of spatial dimensions considered, suggesting a deeper connection between the values of these constants and the underlying structure of spacetime. Moreover, recent advancements in timekeeping, such as the development of optical clocks, have reached such precision that they can test the constancy of fundamental constants over time, potentially revealing variations that could offer insights into new physics beyond the standard model. As we continue to explore these enigmas, we must ask ourselves, are these constants truly universal, or are they emergent properties arising from deeper, yet undiscovered principles? Do they hint at the existence of a multiverse where different regions possess different sets of constants, leading to a myriad of possible realities? In contemplating these questions, we are reminded of the delicate balance that allows the cosmos to exist in its current form, and we are invited to reflect on our place within this grand tapestry. The study of universal constants thus becomes not only a scientific endeavor, but also a philosophical journey, challenging us to consider the fundamental nature of reality and our role as observers within it. Universe anisotropy. The cosmos, often perceived as uniform and isotropic on grand scales, a notion encapsulated in the cosmological principle, may conceal subtle anisotropies that challenge this foundational assumption. Anisotropy implies directional dependence, suggesting that the universe might exhibit variations when observed along different axes. The cosmic microwave background, CMB, the residual radiation from the Big Bang, serves as a canvas where such anisotropies can be examined. Experiments like the Wilkinson Microwave Anisotropy Probe, WMAP, and the BOOMERANG experiment have mapped these temperature fluctuations with high precision, revealing minute variations that offer insights into the early universe's conditions. These observations have placed stringent limits on large-scale anisotropies, indicating that if they exist, they are exceedingly small. However, recent studies have hinted at possible anisotropic signatures in the universe's expansion. For instance, analyses of the CMB have been used to constrain the level of anisotropies at early times, examining how the approach back in time to the singularity is altered in an anisotropic universe. These findings challenge the cosmological principle and suggest that our understanding of the universe's large-scale structure may be incomplete. The implications of a fundamentally anisotropic universe are profound. Could such anisotropies influence the formation and distribution of galaxies, clusters, and the cosmic web? Might they affect the propagation of light and the apparent isotropy of the CMB? Furthermore, how would an anisotropic expansion impact our measurements of cosmological parameters, such as the Hubble constant and the inferred presence of dark energy and dark matter? These questions invite us to reconsider the uniformity we have long ascribed to the cosmos. As we probe deeper into the universe's structure, we must remain open to the possibility that anisotropies, however subtle, could unveil new physics beyond the standard cosmological model. The pursuit of these mysteries not only enhances our comprehension of the cosmos, but also challenges us to question the very principles that have shaped modern cosmology. In this quest, we are reminded that the universe, in all its vastness, may still hold secrets that defy our current understanding, urging us to explore with both rigor and wonder. Wormholes. Theoretical passages through space-time, these enigmatic structures, often referred to as Einstein-Rosen bridges, propose a connection between disparate points in the universe. Rooted in the equations of general relativity, wormholes emerge as solutions that tantalize the imagination with possibilities of shortcuts through the cosmos. A wormhole can be visualized as a tunnel with two ends, each at separate points in space-time. The concept suggests that if such a structure exists, it could allow for instantaneous travel between its endpoints, regardless of the spatial distance separating them. This idea challenges our conventional understanding of space and time, introducing notions that border on the fantastical. However, the theoretical existence of wormholes is fraught with complexities. For a wormhole to be traversable, it would require the presence of exotic matter, substances with negative energy density that violate known energy conditions. The Casimir effect, a quantum phenomenon, provides evidence that such negative energy densities can exist, but harnessing this effect to stabilize a wormhole remains purely speculative. Moreover, even if a traversable wormhole could be stabilized, questions arise about its stability. Would the passage of a single photon cause the structure to collapse? Could such a tunnel withstand the tidal forces inherent in its own construction? These inquiries delve into the heart of theoretical physics, where the boundaries between science and philosophy blur. The implications of traversable wormholes extend beyond mere transportation. They touch upon the nature of causality and the potential for time travel. If one end of a wormhole were accelerated to near light speeds and then returned to its original position, time dilation effects could create scenarios where time loops back on itself, challenging our understanding of temporal order. As we ponder the existence of wormholes, we must ask ourselves, are these structures genuine features of our universe or merely mathematical curiosities? Do they offer a glimpse into a deeper understanding of space-time, or are they mirages born from the limitations of our current theories? The exploration of wormholes invites us to confront the mysteries of the cosmos, urging us to expand our perceptions of reality and consider possibilities that lie beyond the horizon of our understanding.